Okay, good morning to this last morning of this amazing meeting, and the first talk today is given by Emmanuel Saridakis, and he will talk about tension in cosmology. Are we approaching new physics?
Thank you very much, Susanna. I don't think I will lead that, right? I have a loud voice. So good morning, everyone. We're going to explore the tensions that we're facing in cosmology, and we're going to discuss whether we're approaching new physics. The beginning of the talk, it will be a pedagogical introduction, and then I'm going to sketch you all possible solutions. So the first thing that I want you to take back home is the following. The history of physics, but the history of science in general, is a history of tension. So we have some observational data. We make our theories to explain the cosmos, the universe. It works fine, but then as technology advances, it allows us for new, more accurate data, that this data puts our theories into questions. And we need to modify our theories. And then we get modified theories that can explain the universe until the advance of technology allows for new data that put our theories into questions. So this is one basic thing that we must understand, and then we can say, okay, we are living now in the time of tensions. So are we approaching new physics? Do we need to change our picture for the universe? So let me just sketch you going back. So the first cosmological and epistemological model that we had is the Aristotelian Ptolemaic model. And actually this model was so successful and so in agreement with observations that was valid for more than 1,500 years, right? You know the details of that. The Earth is the center of the universe, then we have the planets rotating around that, and the stars, and all this is made by four elements: earth, water, fire, and air. And the heavens, the sky itself, is made by the fifth element, the quintessence, right? So this was a concrete, holistic model in agreement with observations. Of course, it was completed by the works of many other people, from Ptolemy, Archimedes, Sosigenes, many other Greek scientists, until the advance of technology in the Middle Ages, mainly in observations made by the Islamic school in Uzbekistan today, but also in China and India, and this put into question the details of the Aristotelian Ptolemaic model. However, it was in the 1600s where Bragg and Kepler spent 30 years of their lives to observe the motion of the planets, and now is the first time that we establish heliocentric and elliptical orbits, right? We had a huge amount of new data. At the same moment, Galileo was the first guy to perform experiments in gravity, and he found, for instance, that all bodies fall with the same speed independently of the mass, while, in the Aristotelian model, heavier masses fell more quickly. By the way, he was the first guy that made the thought experiments, and Gedanken experiment. I don't have time to talk, probably we can talk on that in the coffee break, that Einstein used a lot, as you know, later on. Okay, and then we come to Newton, and Newton said that the way that I was possible to look very far away is that I was sitting in the shoulders of giants, meaning Kepler and Bragg and Galileo. So Newton put all this observational and experimental data together, and he built the theory of gravity. And this is for the first time that we understand that in order to have a theory for the motion of the planets and the stars, so in order to do cosmology, we need to have a theory of gravity, because gravity is the director of the universe evolution, right? So he realized that it's the same force that makes apples falling on Earth and planets rotating around the sun, the force of gravity. This theory, Newtonian gravity, worked perfectly, and it could predict all motions of the planets in the solar system until in 1859 we observed the anomalies in the Mercury's motion, right? Now, when we learn in school, we say, okay, we measure the anomalies in the Mercury's motion, so Einstein built the general theory of relativity. However, look, this observation was done in 1859. General relativity was put forward in 1915, 60 years after. So for 60 years, This means 2 generations of physicists were living in the years of tensions between our theory, Newtonian gravity, and observation. So this is not, the solution of tension is not an automatic procedure. The same goes with the other experiment, the Michelson-Morley experiment. We say, okay, the Michelson-Morley experiment, Einstein explained it with the special theory of relativity. It took place in 1887. Special relativity was put forward in 1905. So again, 20 years people were trying to explain that. And as you know, GR was the solution to both these tensions, and mainly the anomalies in the Mercury's motion. This is the theory, we all know that. However, this was the solution to the tension. It was not the only effort. And I want to mention here that there were 2 directions. The majority of physicists believed that Newtonian gravity was correct, but there was an extra planet between the Sun and the Mercury, the Vulcan, that in the framework of Newtonian gravity was causing the anomalies in the Mercury's motion. So, most people trying to find a planet that we had not seen, so in a sense, a dark planet, that in the framework of Newtonian gravity was causing the anomalies in the Mercury motion. But as you know, the solution was not a dark planet, the solution was modified gravity, general relativity. However, even for the fewer people that tried to modify gravity, we had many attempts that usually we forget because we know only GR. Actually, all good physicists of the time tried to build a theory of gravity. So we had, first of all, modifications of the Newton's law, or we had the inverse cube law, or extended inverse square law by Simon, Newcomb, and the others. Now, Kelvin and Lorentz also built new theories of gravity, trying to explain the anomalies in the Mercury motion. Nostrom, his theory, I advise you to go and search for them. They were really nice. Actually, he had 2 versions of the theory. And even Einstein built a modified gravity theory that was a scalar theory of gravity before making the tensor theory of gravity, which is general relativity, right? So all these were efforts from the best physicists of the time, and of course, in the end, we know that general relativity was the correct one. So, in the 20th century, we had a huge amount of observations. You're all familiar with that. We now know the standard model of particle physics, the dark matter sector, the cosmological history, Big Bang, inflation, radiation, matter, dark energy eras, and this is the composition of the cosmos today. You have all heard about this. So, GR is consistent with these observations. However, during the 20th century, exactly because of these observations, we had a series of paradigm shifts. Approximately every 20-30 years, our picture for the universe changes. So, let me sketch you here. For instance, in the beginning of the 20th century, we're transited from the infinite to static universe. Then, with Hubble and the others, we transited to the expanding universe. You see a paradigm shift. Our picture for the world changes. Then we change to inflationary Big Bang because we had new data. You need to put inflation in your theory. Then we have the introduction of dark matter, so CDM. And then in the late 90s, we had the introduction of the acceleration of lambda CDM. So you can see that every 20-30 years, our picture for the cosmos changes. And this is in accordance with all history of physics that I told you, from Aristotle to the Middle Ages, Brahe, Kepler, Galileo, Newton, Einstein. So the question is the following: are we living in this situation today? Now, let me summarize. We all know that the standard model of cosmology is lambda CDM, cold dark matter, and a cosmological constant, plus inflation. By the way, inflation is an external input in your theory, right? Some people call it a part of lambda CDM, but in principle, it's a different thing that you need to put it inside. So this is the theory. The Friedman equations, of course. These are the fluids that you put in the universe, and this works perfectly. It can describe the universe at the background level and at the perturbation level. So at the background level, as Germano said, we are using homogeneity and isotropy. This is the Friedman equations. You see here you have the essence of general relativity. On the left-hand side you have the geometry of the universe. On the right-hand side you have all the matter content of the universe. So the matter and geometry are connected. And you make predictions for the background-related quantities like the Hubble function, the density parameters, the dark energy equation of state parameter. And then you go to the background data, supernova, BAO, CABC parameter, cosmic chronometers, all data that are affecting the background, and you fit your theory, right? This is how we're playing this game, and of course, then you can go to perturbations, so you start looking at the universe in a more detailed way. You zoom in, and you start observing deviations from homogeneity and isotropy, and you know also all the theory. So we parameterize that with matter over density. This is a guy in a completely homogeneous isotropic universe. This is 0. In the real universe is not. Delta is given by this expression. So for instance, if you perform scalar perturbations, all these are very easy and standard things. This doesn't work a lot. Probably we should reduce the light. Anyway, so this is the equation that determines the evolution of perturbations. And then you can define some observables like the growth rate and the growth index here. And an important observable is this F sigma 8, which is actually the time-dependent root mean square fluctuation of the density of the matter field within spheres of radius 8 megaparsec. Why 8 megaparsec? Because we want to be in the linear regime, right? So you take these spheres and you count galaxies. If the universe was completely homogeneous and isotropic, this would be 0. But in the real universe, it's not. So you measure this guy here, but if you go back, this is related with your theory, and especially to the effective Newton's constant. So you start to observe the universe at the perturbative level. And lambda CDM works perfectly at this level as well, right? We can describe all the last scale structure of the universe, all the spectrum, etc. However, now we are entering in the 21st century, and we have the technology to do amazing observations. Cosmology is actually an accurate, a precision science now. 20 years ago it was not like that. Cosmology was considered a last chapter close to philosophy and all this stuff. But now it's a science. We have a huge amount of data, and actually most people believe that the 21st century, in this audience I can say that the 21st century belongs to astrophysics and cosmology in a sense that 20th century was belonging to the nuclear physics and particle physics, right? So it's our time. We have a huge amount of data. We have more than 100 space satellites, telescopes in space, and of course we are building now, especially here in Chile, huge Earth-based telescopes, right? So we have a huge amount of new data. And the question is, are these new data bringing tensions that will lead to our change of the world? So I will sketch some of them, and of course we can discuss many of them. GR is not normalizable. This is a theoretical issue. This is not related with observation. We cannot quantize general relativity in the way that we quantize, for instance, electrodynamics. So this is a serious problem. Usually we put it under the carpet, but it's there. Of course, the cosmological constant problem. Why the value of the cosmological constant is 120 orders of magnitude smaller than the one we expect, right? And here, of course, we don't know what that matter is. Still, inflation. How do we describe inflation? We know the kinematics of inflation. We know what inflation should be, but we don't have a concrete model. And of course, H0 and F sigma A tension. I will talk on this in detail. But in the literature, you can find many other tensions. So this is what I want you to take back home. There are many tensions. Anomalies in the CMB, dipole, quadrupole, the lithium problem, the alpha-Lyman forest, and many other issues, but these two tensions are the most severe. And let me start from the basics. GR, right? Just take what we learned in school, how to quantize electrodynamics, go to do that here, you are going to get destroyed. You cannot do that. So there is a problem here. The theory of gravity cannot be quantized, although we know that the matter, or the standard model of particle physics, is quantum, right? Now, the cosmological constant problem, very simple calculations. You just take all possible particles, because in the vacuum you have all this creation and annihilation. If you put down the numbers, you find that the vacuum energy should be 120 orders of magnitude larger. Actually, this is the worst error in the history, not only the history of physics. But by the way, I was giving a talk somewhere and someone asked me, but believing that the Earth is flat is an infinite error. So anyway, but this is something really serious here. So let me come to the H0 tension, although you hear from many other people. So H0 is the value of the Hubble parameter today, right? So we have two ways to estimate. The first is from Planck data, so from CMB data, you estimate, you know, the CMB spectrum is sensitive to some parameters, so you can fit it and estimate the value indirectly for H0, and we obtain 67. Now, you can directly measure H0 by observing the Cepheid galaxies and how they move in a model-independent way. And in this direct way, you observe 74. Here is a plot, I don't know if you can see all the measurements of H0, and here you can see this pink line, the CMB Planck related values, and these are all the direct values. You can clearly see that these are higher, and actually the error goes worse with time. So we are now in 5 sigmas away, right? So the first observation, I think it was around 2012, here we started seeing the tension. So we are around 10 or 8 years in this change in time, right? So it's a small interval. Remember the history of physics. So how you can solve this? Of course, you need to change something, and you can change all the possibilities. You can put higher number effective degrees of freedom. You can assume dynamical or interactive occurrence, or, and this is what I will talk in this talk, you modify the graph. Okay? Now, in principle, also someone else showed this equation in this conference. So, you see, is that guy, that theta. So, in order to solve the tension, either you need to change the sound horizon. So, this is considered to be early universe solution because you change something in the early universe, or you could change that guy here, which is the integral in the angular diameter, which is considered to be a late time solution. But you can have both. So this is what people are doing to solve the H0 tension. Now, there is another tension, although less severe for the moment, and it's the sigma A tension, and this has to do with perturbations. So what is sigma A? Remember, this sigma 8 and F sigma 8 quantifies the amount of clustering that you have. Now, what is this tension? Is the following, that the amount of matter clustering that lambda CDM predicts and the amount of matter clustering that we observe do not coincide. Actually, we observe less clustering than expected, right? Of course, there is a discussion whether there are some systematics here or whether we're double counting things, etc., but most physicists believe that there is something here. And again, in order to solve this tension, you need to change something. You can change the early universe, you can assume hot dark matter or that matter that clusters differently, or again, modified gravity. Now, why I prefer modified gravity is because you modify gravity not only to solve the tensions, you have many other arguments, right? So, in the literature, there are more than 100 solutions for these tensions. Of course, there are some reviews. We also wrote 1-2 reviews. So you can have all kinds of things, holographic dark energy, neutrino interactions, modified gravity, of course, and any other models. You can see that in the literature, in some reviews, and of course, some modifications of gravity. By the way, the fact that we have 100 solutions for the tension means that we don't have a solution for the tension, right? So, this is the one of the review, and we're preparing another one on all these issues. The important thing here is that you must follow some orders in order to solve the tension, because usually when you solve one tension, you make the other one worse, right? So you want to increase H0, but without spoiling the successes of lambda CDM cosmology, because we know that lambda CDM has a lot of successes. The fact that at late times you obtain a higher H0 should not be a cause to destroy all your theory. And of course, when you make that, you should not make sigma A tension worse. So, let us see kinematically, what do we need to solve the tensions? So, naively, you could say that in order to solve H0 tension, I need to increase the Hubble parameter today, obviously. So, I need to add some extra terms in the Friedman equations, in principle. Now, in order to solve the sigma I tension, then you go to the perturbations, and here you can see that the behavior of delta. So remember, I want less clustering. So I need to change something here, and here there are two ways. The background H, the background evolution, is present in the perturbative equations, of course, or the effective Newton's constant. In modified theory of gravity, the Newton's constant is not the one that you start with. Okay, so these are the kinematic things that you need to follow. Now, in this talk, I will focus on modified theories of gravity. First of all, because modified theories of gravity have the advantage that are closer to the quantum regime. So you modify GR because it's only normalizable. But also you solve the tensions. How? Again, qualitatively. A larger H0 means faster expansion. Now, if you build a theory of gravity that is weaker at particular scales, weaker gravity means faster expansion. So this is the underlying mechanism. However, as you know, gravity determines the amount of clustering. We want less clustering than expected. So again, weaker gravity means less clustering. So qualitatively, you can see how modified gravity could solve the tensions. But what is gravity? So let us come back to the basics of GR in order to see what we are going to modify. So this is the general theory of relativity. We must understand the following. In this theory, there are some inputs that were put by Einstein in order to have theoretical consistency. There were some inputs coming from observations, okay? And were some inputs completely arbitrary. So, for instance, let me go back to one. Diffeomorphism invariance, as Eduardo always asks, it's an important theoretical requirement. Your theory must be diffeomorphism invariant, right? So you want this. Now, space-time dimensionality is formed. This is an observational principle. There is nothing fundamental about that. In the scales that we're doing observations, yes, the world seems to be four-dimensional. However, there is nothing fundamental about that. How do you know that on the underlying level the space-time dimensionality is formed? So this, you have a well guess, but this is observational. Geometry equals curvature. This is the main idea of Einstein. This is a completely arbitrary assumption. It works, but it's not the only one. I will come on that later on. Now, the fact that even if it's curvature, your Lagrangian is linear in Ricci scala. Why? I guess you are all familiar with the history of GR. Einstein first found the equations and then the action. Now, in building the equations, he said, okay, in the left-hand side I will have something geometric, in the right-hand side something concerning the matter distribution. So he built the matter energy momentum tensor, and on the other side he put the Einstein tensor. Einstein insisted that the field equation should be second order in order not to have the Cauchy problem and all this, you know, as we say today, this orthographic ghost, etc. This is an efficient condition, but it's not necessary. We now know that if your theory is second order, then you don't have problems. But if your theory is higher order, it doesn't mean that you have problems. You may have, or you may not. Because as we know, you can have transformations like conformal transformations, and what you think that is higher derivative is just an extra degree of freedom with second order field equation. That's why Einstein missed Evo-Var gravity, because he thought that it was problematic. But we know now that Evo-Var is not a fourth order theory, it's not wrong, it's an extra degree of freedom. So this is also an assumption that your Lagrangian is linear to the Ricci scala. The Lagrangian found by Hilbert, actually with 3 days difference, we know all this. Now, metric compatibility, that there is, as we say now, zero non-metricity. The covariant derivative of the metric is zero. Again, this is an external input coming from observation. It's a well guessed, but this is an assumption. There is an argument by Einstein, because you know, if you have non-metricity, then if you transform a vector, the vector changes its length. So Einstein has a very nice argument that if our world had non-metricity, then the redshift will be different according to different dimensions, different directions. So he enforced that to be zero. Again, there is a good observation at him for that, but there is nothing fundamental. And the same goes on with the equivalence principle. There is nothing fundamental with that. This is an experimental principle. At the scales that we observe, yes, equivalence principle seems to be correct. But there is nothing fundamental on that. And the same goes with Lorentz variant. At the scales that we are making experiments, Lorentz variant seems to be the case. So in summary, in GR, you have things that are necessary for theoretical consistency, without things that are coming from observations, but there is nothing fundamental, and of course, you have things that are completely arbitrary, right? So, what does it mean to modify gravity? Is to start breaking this one by one. And of course, there is another argument, let's say. You know, here on the left, you can see the most successful theory of humanity, quantum electrodynamics and quantum electroweak theory. This works perfectly up to the 10th degree of accuracy. Now, on the right-hand side, you have general relativity. So, as you can see, there are not many chances that this is the end of the game. Right? This is a too simple theory to be the theory of nature. But there is, you know, in the literature, just to be fair, there is a school of thought that probably we need to reduce this to a thing like that. And actually, this is what we were discussing. There is a, how do you say, there is a principle in the scientific community that nature in its foundation is simple. This is an idea of Pythagoras. Pythagoras was the first guy that said that nature is simple, and if we have two theories explaining the same thing, we must choose the simplest one. And this passed through Aristotle to the Middle Ages to Occam, and then we have this Occam nature. But how do we know that? How do you know that the nature is simple? Let's do research, and if nature is simple, okay. If it's not, again, okay, you cannot go a priori with a philosophical principle. And actually, to tell you the truth, as we dig deeper and deeper, nature doesn't look simpler. This is not simpler, right? We start from molecules, atoms, protons, neutrons, quarks. There's nothing simpler. I would say that the level of complexity increases when we dig deeper and deeper. But okay, so let's forget about that and start doing physics. So, in the literature, you can find, as Germano showed yesterday, hundreds of modifications of gravity, coming by breaking one by one these assumptions. For instance, you can consider extra scalar vector tensor degrees of freedom, going to all these theories that you know, scalar tensor, Brasdicki, and Proca theories, etc. You can insert higher order invariants, f of var gravity, and f of g, Lovelock theories, etc. You can go to higher dimensions, like in string theory or in Bragg models, or you can consider different geometry. I will focus on that in putting torsion into the game. Of course, you can go to other modifications, even more advanced things. For instance, this emergent gravity, or this one of my favorite one, although as a community we have not understood anything, that gravity could be an emergent phenomenon. Like temperature, for example. Temperature does not exist fundamentally, but it arises as you increase the level of complexity. There are many schools thinking that probably we are in the same direction. Gravity does not exist at the fundamental level. So, all these are theories that you can find in the literature, and I will talk mainly on some of them. So, and relating to the tensions. The first, the prototype of modification of gravity is scalar tensor theory. So you introduce a scalar field. You are all familiar with that. In the action, this is a equation of motion. Then if you go to spherical symmetric solution, you are using the solar system test in order to fit your parameter. And later on, although in the original Brasdicki theory you didn't have a potential, later on you have a potential. And these are the Friedmann equations. You see, now they are modified because these scalar fields plays a role. And of course, you can use this theory to obtain the thermal history of the universe, and it is very efficient. Then you can go to even more general scalar tensor theories, and actually Hordenski in 1974 asked himself, what is the most general theory with one propagating degree of freedom and curvature terms? And he found out Hordenski theory, We heard many talks on that, but this theory was forgotten because Hordensky abandoned physics to become a painter. And actually he became a good painter, he made a lot of money, and actually this theory was rediscovered in the framework of Galilean theories, and generalized Galileo is the same theory with that. And this is Hordensky cosmology, so you assume FRW metric, these are the Friedman equations, and of course you need to go to perturbations, and do perturbations. These are very simple things, and these are the two conditions for absence of instabilities. And even you can go beyond Hordensky and introduce extra terms. By the way, what are beyond Hordensky? Because Hordensky proved that the theory of gravity, one propagating extra degree of freedom, is Hordensky gravity. How can we add new terms? And the key point here is that here you are adding a second extra degree of freedom, but it's not propagating. So strictly speaking, it is beyond Hordensky, because in the end of the day you have one propagating degree of freedom, but it's more general theory. Now, let me show you how in some papers we solve the tensions with these theories. So here, of course, you have a huge freedom. In Hordensky gravity, you have many extra functions. So the idea is the following. At early times, at the CMB times, we need to coincide with lambda CTM. But at late times, we need to put extra information in the Friedman equation to solve the tension. And if you select your functions accordingly, you can obtain that. So you solve the tension. What is the mechanism behind that? Is that you obtain a weaker gravity. So if you plot this ratio here, you can see that at suitable intermediate scales, gravity is weaker. So this leads to faster expansion. So this is how Hordensky gravity solves the tension. And this has been found in the literature by other people too, with different kind of Hordensky models. Now, you can also go to biscalar theories of gravity. So now we are playing with box R. This funny thing is box and nabla R square. So here, these theories, these modified gravity theories, have two extra degrees of freedom. And you can see that by making a double conformal transformation, you have two extra scalar fields. These are very good in explaining the thermal history of the universe. And by choosing particular functions, this is the idea. Don't pay attention into the detail. What we want is to increase the Hubble parameter by putting extra terms, suitable extra terms in the Friedman equation. And you can increase H naught. Now, there is another modification of gravity in the literature, the running vacuum theories, and in these models, you just upgrade the cosmological constant to be running, depending on H. So these models here, this is the effective dark energy density. It depends now on the Hubble function, and with these models, you can also solve the tensions. Okay? Now, in the last part of my talk, okay, I will talk about the geometrical modifications of gravity. Actually, you know, in Plato's Academy, which is considered to be the first university in the world, in Athens, it was a general university. But in the door, it was written that those that do not know geometry should not enter. Just to give to people the idea how important is geometry in order to understand the cosmos, the universe. Whatever you want. If you want to do biology, chemistry, philosophy, geometry is the fundamental square. So, using geometry, Einstein was the first to understand, and this is the essence of GR, that gravity is a geometrical force. So, in general relativity, matter tells space-time how to curve, and the curved space-time tells matter how to move, right? So, in this theory, gravity is geometry, geometry is curvature, so gravity is curvature, right? Very easy things. Technically, how you are doing that, you assume the Leibniz-Vita connection. So the Leibniz-Vita connection, because it's symmetric, by contraction, it has zero torsion and it has only curvature. Okay? General relativity works perfectly. Now, later on, 12 years later, Einstein found an equivalent way to describe gravity using torsion. Initially, his motivation was the following. Gravity is described by curvature, so if electromagnetism is described by torsion, using geometrical concepts, curvature and torsion, we could have a unified theory of gravity and electrodynamics. However, as he found, torsion does not describe electromagnetism. Torsion is an equivalent way to describe gravity. So in this theory, gravity is still geometry, but geometry is torsion, so gravity is torsion. And technically, you obtain that by using the Weisbach connection, which, by construction, it has only torsion and zero curvature. You see, and this is something, of course, many of you are experts on that. Curvature and torsion are properties of the connection, not of the space-time itself. So if I have a space-time, a manifold, and a metric, you know, metric is from the Greek word to measure, eh? You have a metric, helps you to measure angles and areas and all this stuff. So if I give you a manifold with a metric, and I'm asking you, what is the curvature and torsion of this space-time? What is the answer? The answer is that there is no answer. In order to find the curvature and torsion, you need to define a connection. A connection is completely dependent concept than the metric. So the connection is related to the parallel transportation. You need to have a rule how to parallel transport the vectors. And in Einstein's autobiography, he says that he was sitting in his office and suddenly he understood that motion in physics means connection in mathematics. You cannot move particles if you don't have a connection. You need to have a rule how one particle or a vector or whatever should go to the next space-time point. And this is independent. The way you define your parallel transportation is independent of the way you define your metric, right? So there are infinite connections with infinite choices of curvature and torsion. Amongst them, there is only one, the Leibniz-Civita connection, which has zero torsion, and there is the Weisbach connection, which has zero curvature. Okay? Now, in general, not in very general, I'm still in simple geometries, I'm not going to Fincher or other geometries. So you have a general affine connection, you can split it to three terms, the Leibniz-Civita connection, a term related to torsion, and a term related to non-metricity. You are all familiar with that. What does it mean? If I have curvature, then this means that my parallel transportation, through a parallel transportation, my vector will change the angle, and this change of angle is curvature. Now in torsion, if I do parallel transportation, the parallel elements do not close. And in non-metricity, as I told you, the length of the vector changes. Okay? So in principle, we have more than one way to describe gravity. Even if we assume, even if we, agree with Einstein that gravity is geometry, we have more than one geometry. Why Einstein kept the Riemannian geometry? Because in 1915, people only knew Riemannian geometry. Torsion came into the game in 1919 with the works of Poincaré, Catan, Weisbach, and the others. So Einstein chose the first non-trivial thing that he had, but this is not the only case. We need to agree on that, and this is a back-home lesson, okay? So Riemannian geometry works, it's perfect, but it's not the only choice. Now, let me just sketch you the simple idea. So this is the metric. In these formulations, I will talk about some very simple theories. We are using the tetrad fields. This is the four orthonormal fields of the tangent space for the basis. These tetrads or V-binding fields are related to the metric with this expression. And of course, if I have a general connection, these are the curvature and torsion tensor. And of course, I can express the general curvature scalar in terms of the Leibniz-Civita scalar and the torsion scalar and a total derivative. So you can immediately see that if I use this guy or this guy as a Lagrangian, because they differ by a total derivative, it will give the same equations. So in torsional theories, you obtain the torsion scalar in a similar way that in curvature theories, you obtain the Ricci scalar from contractions of the Riemann tensor. Here, from contractions of the torsion tensor, you obtain the torsion scalar. And this is your Lagrange. Now, I will give you another hint in favor of torsion, and this is what people understood in the 60s in order to build the gauge theory of gravity. So, if you want to formulate a theory as a gauge theory, we apply the gauge principle. This is that we are all familiar with from electrodynamics or electric weak theory. So in this theory, you take the global symmetries of your theory, you replace them by local ones, and in this way, you have the group generators of these procedures, and later on, that's why it's important to formulate your theory as a gauge theory. Later on, if you want to quantize your theory, it is these compensating fields that are going to be quantized, right? And we know that these procedures work perfectly for SU3, cross SU2, cross U1, so for the electron-weak and strong interactions. And people try to apply that in gravity. So, very simple, let's apply this Weil-Yang-Mills Gates principle to the Poincaré symmetries of the theory, and you find Poincaré Gates theory of gravity. Now, in this theory, you find that you have both curvature and torsion. So, in a sense, torsion is the field strength of the translation group, is needed if you want to formulate your theory as a Gates theory. And of course, this procedure is independent of extra assumptions that you are making, even if you assume invariance under supergravity transformation or conformal transformation, Weil transformation, you obtain respectively supergravity or conformal gravity or Weil gravity. In all these theories, you have both curvature and torsion. So, let us start with the simple, the teleparallel equivalent of general relativity, although you have heard many things about that. So, we are using the Weisbach connection. This is the torsion tensor. Contraction of this gives you the torsion scalar. This is the Lagrangian of your theory, and this theory is called teleparallel equivalent of general relativity because it gives you the same equation. By the way, the word teleparallel in Greek means distant parallel, right? So it's the way that Einstein was not good in names, like in relativity. So he named this theory teleparallel theory because it's the way that we define parallel at the distance. Now, although general relativity is completely equivalent with the teleparallel equivalent of general relativity, if you start modifying them in a naive way that we're doing in the literature, take R to F of R or T to F of T, then you don't have equivalence anymore, right? So although we started with two equivalent theories, by modifying them, you don't obtain the same universality class. You obtain different theories, right? It's not that one of them is correct and the other one is wrong. Both are correct. There are different theories of gravity, and this is the famous M of T gravity. These are the field equations. If you are going to do cosmology, you assume homogeneity and isotropy, and these are the Friedman equations. Again, these are different from F of R gravity. And an important advantage is that these are second-order field equations, because the torsion scalar in FRW is just 6h squared. Now, you can take F of T gravity at the background level. You define the effective dark energy, density, and pressure. So these are now have geometrical origin, but torsional origin. And of course, you can fit with the data, and you can also go to perturbations. So we have a theory who can do all things that we're doing in GR, right, or in F of R gravity. Perturbations, background, expansion, etc. And of course, then you need to find viable models, so models that are in agreement with the data. And for instance, we have three models, a power law model or exponential or square root exponential. In these theories, you find the effective Newton's constant. It's important that in modified gravity, you always find an effective Newton's constant. And the idea is, okay, we have a modified theory of gravity. Can we use that to solve the tensions? Remember, we need to play with the terms in order to have extra terms in the field equations and also solve the perturbative equations by playing with the delta equation. So again, we want at the early times to have full coincidence with lambda CDM and change only the late times. So we add small corrections at late times, and the important thing is here. This is the effective Newton's constant in someone else has a talk, yes?
Question, the effective Newton constant comes with the f of t term or in the simple teleparallel gravity?
No, in f of t. In simple teleparallel gravity is identical with GR. It's the same completely. In f of t, here you obtain the derivative of t at the denominator. So the idea is, okay, let's play with f of t forms in order to have a weaker gravity. And of course, if you put all this in the delta equation, in the end of the day, you found that you can have some small corrections to teleparallel gravity, so small corrections to GR that can solve the tensions. And this is what we obtain in a series of papers. First of all, you obtain a higher H naught because you have a weaker gravity, and a smaller F sigma A because you have a weaker gravity. Okay? And of course, in the end of the day, you have to use all data. It's not, these are very simple curves, but if you do the whole analysis, the Bayesian analysis, you found that you solve the tensions. Now, let me stress here an important thing. in f of t gravity, you can have viable theories of gravity in which the Newton's constant is weaker. This is not possible. It's not easy to be obtained in other theories. For instance, in f of r gravity, if you go and find the effective Newton's constant, now the Newton's constant is also scale dependent, apart from time dependent. But if you want your theories to be free of ghosts, then this is larger than 1. So in viable f of r theories, typically you obtain stronger gravity. So you cannot solve the tensions. While in f of t gravity it's possible. Okay, since I'm running out of time, this is the last issue that I want to talk about, and Maria Jose is going to have a whole talk on these non-metricity theories. So, I told you in the beginning that we have curvature, torsion, but there is a third way. It's to consider non-metricity. So, in this case, we can choose, you see here is the general affine connection, Levi-Civita, contortion terms, and non-metricity. We can play with this guy. This is the non-metricity term, and we can define this. You see, this is the covariant derivative of the metric. Q is 0 in GR. But in general, it cannot be 0. So, torsion tensor, curvature tensor, non-metricity tensor, we are going to set this to 0, and this is called symmetric Telepara gravity, and from the non-metricity tensor, we define the non-metricity scalar. So this guy will be our Lagrangian now. So if we want to extend this theory, because if you use only Q, your theory is equivalent with GR and TGR. If you go to f of Q, you have a new theory. So these are the field equations. And if you want to do cosmology, these are the FQ cosmology Friedman equations, right? In Q, the non-metricity scalar, in F or W is just 6h squared. So these are the perturbations now. Okay, I have a theory, I need to perturb that. So I perturb the non-metricity tensor, and these are the equations. And of course, this is the equation determining the evolution of matter of a density. Again, this is the effective Newton's constant, right? It's different than GR. And within this theory, we can also solve the tensions. So again, here we obtain a weaker gravity, and in a suitable scale that can help you to solve the tension. So you obtain a smaller f sigma 8 and higher h naught values. Okay? So let me summarize. The first thing I want you to take back home is the following. The history of physics is the history of tension. Full stop. We need to understand that. We have theories, we explain the universe, but then we have new data, and these new data put our theories into questions, and then we need to modify our theories to make better theories, modified theories, extended theories, in order to be able to describe the data. And this goes perfectly until the moment that you have new data that put your theories into questions, and you need to go on and on to better and better theories. Remember, it's not like that the old theories are wrong. Newtonian gravity is not wrong. It's correct. Make any experiment you want here. We are going to verify Newtonian gravity. But GR is a deeper theory, which has, of course, Newtonian gravity as a limit. Okay? So we are deepening our knowledge. And then, since we have a paradigm shift every, say, 30, 40 years, are we living in such an era? And as I told you, we have many tensions. We have a successful model, GR plus lambda CDM, but now we have many, many tensions appearing. We cannot hide them under the carpet. Even if many of them are systematic, there are very curious tensions that we need to solve. By the way, let me tell you here that, you know, concerning lambda, we started measuring the matter density parameter in 1993, 1994. And people were saying for the first moment, look, omega matter is not 1, it's 0.3, so there is something else there. This is what the observationalists come and said. And we used to say them, come on, we know it's a different measurement, measure that again, you must find 1. And it took us 5 years to believe them that there was lambda there. So again, now people that are making observations, they're coming to us and say, look, there is a problem with H naught. We are not finding the same thing with lambda CDM prediction. And some of them are saying, oh, there is a systematic, do it again if you are not careful. But we need to have a different mentality and trust the data. So there is a discussion that some kind of new physics is needed. Of course, it can be anything. Perhaps it's not needed to touch GR, but as I told you, modified GR is needed also for theoretical consistency. That's why in this talk I focused on modifications of gravity. So the idea is the following: we need to build more fundamental, more deep theories of gravity that of course will have GR as a low energy limit, but in general they will be able to solve the torsions. In a sense, and I will finish with that, you know this Plato's allegory that we are sitting as humans in a cave, we cannot go out of the cave, and all we can see are the shadows of things, and from these shadows we must understand the true nature of the universe. Right? We cannot travel outside of our planet or our solar system, but we are clever enough to be able to do cosmology. Remember, all of you, I guess you know the Eratosthenes experiment about measuring the Earth radius. He didn't leave the Earth. He was on Earth, but by making logical arguments and a specific experiment, he was able to measure something without going out of his cave. So the same happens with us. We are here in our lab. So this is a scientist with his laptop doing research on Earth. He cannot explain, but we are clever enough from the shadows of what we measure on Earth to be able to understand the true nature of things. And I think, especially the young generations, you have a lot of work to do. And I'm sure, remember that I told you in Arica in 2024, you are going to live, we are all going to live a paradigm shift. A change from lambda CDM. I don't know if this will be in 5 years or in 20 years, but remember this moment that we are going to live that. So, I end here. Thank you.
Questions? Thank you very much for the nice talk. Anybody?
No.
Maria Jose? I'm sorry, it's morning for me also.
Hi Manos, thank you for your very energetic talk. I have one comment and one question. The comment is, I don't think general relativity is so simple. I think this slide was a bit misleading because if you write Einstein's equations, they are highly, in terms of the metric, they are highly nonlinear, and even if you want to solve like some simple problem of physical relevance like merger of black holes, simulation of that can take months. Yeah, so imagine you want to describe like the universe fully. Regarding the, why do you think it has not been quantized, the torsion, if it is like a field strength of some group?
The curvature based GR. I mean, you cannot quantize that following the standard ways. Torsion, I agree, that's why I put torsion into the game. But without torsion, if you have standard general relativity, you don't know about torsion, you cannot quantize that.
Yeah, exactly. But do you think it will happen the same problem with, like, if you describe, you know, try to quantize the torsion? Yes. I'm not sure if it has been attempt actually.
Okay. Jose Pereira also has made some attempts, but the issue is the following: that if you don't modify that, I'm not sure that you are going. It's possible to quantize that. Otherwise, we will know the answer.
Yeah.
On the other hand, we know from Kelly-Stell from the 70s that if you add higher order terms, higher order curvature or torsion terms, you improve renormalizability. So it's for the first time that we understood that putting higher order, so modifying your theory, it's easier to get quantized. So this is a hint, it's not a proof. It's just a direction that we may follow.
Yeah, and finally, I like what you said, that if we have 100 theories describing something, we don't understand it. Exactly. How do you think we are going to solve this degeneracy of 100?
How to make it, actually I was expecting to ask me about the strong coupling problem.
That's my next question.
No, look, I mean, this is what, as a physicist, we should do. We need to find observables to break the degeneracy between theories. I will tell you one example. I mean, first of all, let me give you the answer. Is to find for new experiments, new observations, completely new. I will tell you one example. Before 2015, we had supernova data, BAOs, CMB, cosmic chronometers, all data that we have in cosmology. And we had, for instance, maybe 100 theories that were passing all the data. Hortensky, Quintessence, all these theories. In 2015, we observed the first gravitational wave. And it shows us that the gravitational wave speed is equal to the light speed, an error of 10 to the minus 15. So with just one data point, we excluded half of the theories because they were not predicted, because in modified theories of gravity, typically you predict a different gravitational wave speed. So for instance, large classes of Hortensky theory were excluded immediately, or these classes that have the G5, just from one data point. So you see, because we were able to see through a new window. So the community will say that, for instance, gravitational waves will be very crucial in order to kill theories. Because you have many theories that pass, it's very easy to obtain supernova and BAO and CMB agreement. But if you start looking at the details with the gravitational wave features and data, then it's hard. So in my opinion, we should find for new, completely different observations that will break the generation between the theories. Because for the moment, it's very easy to say that something is different from GR, but you cannot distinguish between two samples. This is very hard. So the idea is to go to new observations.
Yeah, I hope we can find these observations. Yeah. Well, since you mentioned strong coupling, you presented very nicely, like f of t and f of q very nicely fit cosmology. Yeah. And I saw you have a recent paper on the strong coupling in f of t. Can you say a few words, like very shortly?
Yeah, okay. First of all, let me be fair. Most of these theories, it's not easy to modify GR. In most theories, if you start modifying GR, you find all kinds of problems. Theoretical problems, instabilities, etc., etc. So you have to be very careful. Now, in many of these theories, people are discussing that you may have kind of instability of kind of problem, and one serious problem is the strong coupling problem. I agree that it's a serious problem, and we need to be very careful when we're trying to solve that. However, and this is what I want to point out, GR also has a problem. The non-normalizability is a problem. Okay, some people will say that, okay, we're doing classical things, we do not care. Fair enough. But GR also has a problem. So I agree with you. It's not easy to modify gravity. That's why if we could do that, we could have the solution. So we are in the beginning of the 20th century. We are building theories and trying to understand what's going on. And in the end, through this procedure, we're going to find. Yes, but in the long run, yes, I agree. It's a serious problem in these kind of theories.
A couple of questions. Is there a way of coupling to matter that would be the equivalent of minimal coupling in teleparallel gravity? One that is a recipe that is free from ambiguities? And another similar question is there the analogous of the McDowell-Mansur reaction, some kind of geometrical way of singling out one action between all the possible teleparallel gravity actions?
Okay, now, the matter coupling is an independent issue. It's a big discussion. Even in GR, I didn't mention that. In GR, Einstein assumed what we were saying, that the minimal coupling of matter to gravity. So matter sees only the square root of G. So it does not interact, for instance, with this scalar square, as we are doing today. So this is an assumption, again. Now, in these theories, both in curvature and torsion theories, you can also play with the matter coupling. Remember yesterday, for instance, Francisco talked about possible this F, R, T gravity, and someone else talked about that, or we play with matter Lagrange. So the matter coupling is a whole new issue, and you can incorporate it here. You can have all forms of matter coupling. Now, the way how can you distinguish actions in torsion or geometric theories, for the moment we don't know that. Because you have all possibilities. Okay, some of them are excluded from theoretical consistency. You cannot have parity violation, actions, etc., etc. But still, you remain with an infinite now. See, this is the interesting thing with modified gravity is the following. There are infinite theories of modified gravity. So even if you exclude infinite theories, you remain with infinite theories. So that's a problem. But this is what we are doing as a community.
Okay, anything else?
Thank you very much, Manuel. A very nice talk. Fantastic talk. I have a question. Do you speak about the F of Q gravity theories? Yes, but I have a question. Can be possible to be these theories be compatible with the local constraints, for example, like the weak equivalence principle?
Good. Now, all these theories, okay, all these modified theories, you obtain extra terms in your equations. Now, the idea is that this was the initial motivation. These extra terms will play the role of a cosmological constant and accelerate the universe. Now, the cosmological constant, the measured one, is 10 to the minus 36 electron volts. It's very small. You cannot see the cosmological constant in the solar system or even the galaxy. You need to go to large scales. So all these theories, we are using them in order to obtain cosmological better behavior, right? So at the solar system, they do not play. In the solar system, all experiments verify general relativity. So all the corrections should be less than 10 to the minus 5 in the solar system. So my answer is the following. Yes, they can pass all tests because the modifications is very small at this scales. In order to see these modifications, you should either go to cosmology, so at large scales, or to very strong gravitational fields, which is the black hole. Now, in the black holes, and especially supermassive black holes, all these theories have an entry in the what we are calling the black hole saddle. So if you take these theories, you obtain the black hole solution, you find the photonic sphere, and you find the shadow of the black hole because we have the data from the EXT telescope, then you can find in principle differences. So you need either to go to cosmology or to very strong fields. In the solar system, it's only GR.
Thank you.
Anybody else? I have a final question. It's like a comment.
Very nice talk. Just a comment, yeah, and a question also. In all your discussion, you totally ignore anything that the string theory are doing. So, can you connect any of what you mentioned to? Of course, the string theory is supposed to fix the quantum gravity, blah 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 blah, and they have also speculations about the swampland, and also that apparently has consequences for cosmology, although I don't think it's very good, but okay, so some comments.
Yeah, in the beginning I showed you that there is a different direction of modifying gravity by going to the more fundamental changing like the string theory or Brainwave model. Now, the connection should be the following, because there are some works in the literature, that in string theory, if you do the compactification and you are lowering the scales, you obtain towers of curvature and torsion. So again, torsion is embedded in the string theory, and in these theories you could see them as an effective and a low energy limit of string theory. So there are some works claiming that if you start from string theories, in the end, following particular directions, you can have this series. So that could be one connection. But for the moment, again, these are effective theories at the low energy level.
Okay, so I have now two questions. One is just a comment, but I want to ask you if you agree with my comment. When you mentioned the Hubble tension, initially you didn't mention anything about the model that you were assuming, and both with the Planck estimation and the Cepheid estimation, you're assuming lambda CDM. You agree with this?
Yeah, of course. This is what we were discussing. I think this is a more serious issue in cosmology and astrophysics. That we calibrate our experiments in order to make observations, assuming some models. There are many ways that lambda CDM can reside, many calibrations. So that's why some people are saying, okay, if you input lambda CDM here and there, in the end, you're going to find that lambda CDM is the best model, because you have put it in a very curious way. So yes, this is a severe issue, and this is what we were claiming, that we should look for different things. For instance, the gravitational waves in Light and Virgo are not sensitive on that. So you see, we should try to find new windows that are model independent, completely model independent.
Okay, and you mentioned also that you will see differences with the F of T in the shadow of the black hole. You estimate that future experiments can give a clue about the true theory?
Yeah. I mean, I'm optimist about that, especially as we're going to have even more and more accurate data. Although there are generations with the spinning of the black hole and the modified gravity terms, but I'm optimistic that we're going to find signatures there. No, for instance, in the gravitational waves, we know that considering the number of polarizations, if you observe a third polarization, it's modified gravity. This will be a proof, a smoking gun, because GR predicts only 2. So there, the difference is quantitative. It's not like, okay, I'm obtaining W not -1, but -1.001, and then you cannot distinguish. If you obtain an extra polarization mode, it's a signature of modified gravity.
Okay, thank you very much. Anybody else? So.
What do you think is more probably, modified gravity or a new fundamental field for dark energy?
I don't know. This is what Maria was saying, how to distinguish them. I would say modified gravity, because it will help you to be closer to a quantum world. But this is open, we don't know.
Okay, but what is your feeling about it?
I have a favor in modified gravity, but this is just a favor. Let's see what nature will tell us.
Okay. Thank you.
So we thank the speaker again.
No la tienes en pendrive, ¿no? No. Ya, pues el correo nomás. O sea, si es más rápido, sí, pero si no...
¿Vas a usar el micrófono?
Solamente...
Okay. Okay, our next speaker is Joel Saavedra from Pontificia Universidad Católica de Valparaíso, and he will talk about PV phase transition, Einstein gravity, and holographic dark energy, and a little more.
Thank you. I would like to thank to the organizer for the kind hospitality and also for the warming conference. I am talking about something different at the beginning. The title is a little bit changing from my talk, but the idea is to introduce a new tension, but a new theoretical tension. because we change and we modify gravity. But when we modify gravity, as Manu said, we introduce some issues, some problems. But nobody cares about this kind of problem. Then I would like to start with the online motivation. At the beginning, we are talking about a very old problem about the Gauss-Bonnet models and some very well-known problem, I guess, in the 60s, about the branch Hamiltonian or multivalue Hamiltonian. What happens when we have a theory that can be described by different Hamiltonians, and then we try to quantize the theory? If we are thinking at the 80 or 70, we know the Witt equation, and we need to do the canonical quantization, and we need the Hamiltonian. After that, we know that there are another way to solve the problem, and the other way is via path integral, and there are some articles that said without the Lagrangian, we don't have quantization. This is an article from Hochman and Shepard. But this problem is still there, and I would like to say some more about this. This is the original motivation of our work. We are working now in a related problem, but it's completely different than the original problem. The original problem is still an open problem, and you will see how we do the transition between different problems. After that, we are talking about the thermodynamics on the horizon in a particle solution in a Friedman universe, and then we move in our approach. Our approach is to say we have a PV phase transition like Van der Waals fluid, but in Einstein gravity. There are so many articles that show the Einstein gravity with a Friedman-Robertson universe. They don't have phase transition, and we have one way to obtain phase transition in this case, and we are using the orographical energy. This is our first point. And the second point is a short view of modified cosmology, because we are doing a changing of the approach in this case. At the end, remarks on some open idea. At the beginning, we start with the, let me tell, economic Einstein-Hilbert action. Not the simplest one. It's an economic way to write the gravity and matter and the interaction between them. And everyone knows this kind of theory can be construed by the Riemann tensor and the connection is a function of the metric. If you write the geometric Lagrangian, you can prove this geometric Lagrangian is up to second derivative of the metric. Then we will have a problem. If we remember about the classical mechanics, when you have a Lagrangian depending on the second derivative, your equation will be of the higher order. But therefore there are something missed here. We need to add one boundary term in order to have a well-posed variation problem. In other case, you need to fix the metric and the derivative of the metric and the boundary. Then you need to put another term here, the boundary term. And after that, we can do the extension. For example, we can think what happens in the higher dimension. And the most natural extension is to think doing this through the modified gravity, FR. And the first approach, Emmanuel said something about the steel paper, when we can put the quadratic correction to the Einstein-Hilbert Hamilton, to the Einstein-Hilbert Lagrangian. But there are some prices. We have the renormalization. We can show this approach is free, but we pay some price, and the price is our equation at the four orders. Therefore, we have a situation a little bit complicated, because we know, or we use, the nature is described by second order equation. If we believe in causality, if we can to relax causality, we can see maybe will be. But the problem is that in this case appears some ghost, some instability, some problem that will be very bad for our theory. Therefore, we need to do something different. we need to change the alpha, beta, and gamma parameters in a very special combination. And when we do that, we obtain the very well-known term, Gauss-Bonnet term. And this term now, when you do the evaluation, you can obtain second-order distribution. And then we solve my problem. And now we have a kind of modification. Therefore, we can try to see, let me try with a toy action. And this toy action is just, I am adding the Gauss-Bonnet term. But when I am adding the Gauss-Bonnet term, again, I need to put some boundary term, completely different than the previous one and more difficult. Then we need to, from the theoretical point of view, we need to work with this, we need to try to deal with this, and when we want to go there, we want to go forward, we need to put also some counterterm in order to have a finite action. But let me try with something simple. One way, very simple, is to say, let me put some well-known model, and we are using an answer for the metrics, we are using a cosmology. Because the cosmology, when we put the cosmology, for example, in the action, at the end, and obtain a kind of classical mechanics. We break the covariant theory, but we will obtain something simple. We can deal with this, and we can show exactly the problem that this kind of theory could be present. Therefore, in red, we have exactly the term that is giving us the problem in the future. And this term came from the Gauss-Bonnet term. Then we can choose our answer, and in this case we are putting the action in D dimension. And when we are trying to do the first one we learn when we are working on the classical mechanics, we write the canonical momentum, and we have a problem here because we have a cubic equation, and therefore we have three possible solutions. And the question is, what happened there after that? Because when we are writing the Hamiltonian, we have three possible Hamiltonians in order to do that. Then we need to say, what is the Hamiltonian for our system? But this problem is a very well-known problem from the 80s by Zanelli, Genoa, and Tentepol. They proposed this toy model. This is a kind of free particle that they don't have a term of potential or interaction. Therefore, this is a kind of generalized free particle, a Gauss-Bonnet free particle. And if we write the Euler-Lagrange equation, we can show there are one conservation law. But when you are seeing the dynamic of this system is changing in a spontaneous way the trajectory. Therefore, here appears some kind of zigzag. And this is a problem because the classical mechanical, we hope the classical mechanical will be smooth. But here we have a kind of different classical mechanical, and the Hamiltonian will be, the momentum will be a cubic momentum, and when we are trying to do the standard problem, like the canonical Legendre transformation, we obtain three possible solutions for the Hamiltonian, and we have some caps where something will be happened there. This kind of action is very well studied. There are many articles trying to see some application about this toy model proposed by Zanelli, Tentepol, and Genoa. And for example, Witcher worked in this problem in 2015, I guess, and he showed the existence of this kind of crystal time. And also, there are people trying to show the Gauss-Bonnet action also has an overphase transition and a kind of Hawking and Page transition. And in this case, they call this novel phase transition. This guy is Edelstein, Kiribet, and Camacho. And also there are more problems here because we can also sum or add some other problem like singular Lagrangian. Also we can try to do this with singular Lagrangian, and we can obtain that singular multivariable system Therefore, there are problems with the Hamiltonian formulation. This Hamiltonian formulation is important because if we want to write the quantum mechanics in the canonical way, we need the Hamiltonian. And then we need to take the classical limit, and we hope to obtain just one classical limit, but here we have 3 possible classical limits. But this problem is solved in some way. There are different approaches in order to solve this problem. The first problem is a simple way to think. We need to generalize the Legendre transformation, because the Legendre transformation is for convex Lagrangian, and this Lagrangian is not convex. Therefore, our approach we need to be different. And in this case, there are some possible solutions. The Legendre-French transformation that is applied for no convex Lagrangians, where they use the supreme of momentum, and they can define one single Hamiltonian. Then, in principle, the problem is solved. You need to generalize the Legendre transformation, and the other way is to consider the phase space production, and using the Dirac program, you have constraints, and you can implement this, and using a kind of generalized Legendre transformation, you can obtain also again one single Hamiltonian, and the problem will be solved. In both cases, at the end, the result is they finish with a single value Hamiltonian. But when you try to do the canonical transformation, because this Hamiltonian must be related by the canonical transformation, they are not related through the canonical transformation. Therefore, at the end, you have again 2 Hamiltonians. At least you have 2 Hamiltonians. We reduce the number of the Hamiltonian, but at the end, I finish with 2 Hamiltonians. Therefore, the problem is exactly not solved. But the main situation in this problem is shared by different models of gravity. For example, if we are writing Lagrange gravity, the most general action that can be written in higher dimension, that when who can give us second order equation, also has this problem. And this problem is for something very simple, because this term is nonlinear. Therefore, we have another kind of implication of nonlinear term here in the Gauss-Bonnet, and also in Laplace at any dimension. In 4 dimensions, we have the Gauss-Bonnet. In 3 dimensions, we have the Einstein-Hilbert. In 5 dimensions, we have the Gauss-Bonnet, and also we have another alternative that is called Chern-Simons gravity. But all these are very well studied. There are a lot of very good property, and a kind of a theory of gravity that we can move forward, and we can try to hope, in some case, to obtain some approach to quantization. In odd dimension, we have Chern-Simons gravity, but here the situation is worse, because besides the nonlinearity at the curvature, we have the problem that the Hessian matrix can have some singularities, and also the symplectic structure can be degenerated. Then the situation is worse, and here there are a lot of pathologies. For example, if we are seeing the article, I don't know where it is, the anatomy of the red and Fariñas, they show in this kind of theory, if you are putting here Fariña Junior, and if you are considering this kind of theory, you can obtain region where the theory is going to catastrophe, and therefore there are isolate region at the phase space. And this is a very nice property, but also is a very difficult property to work there, to work with this degenerate symplectic structure. And Zanelli takes this problem again in 2010, 2002, and tried to do the dynamical reduction of the multivalent Hamiltonian. And then he tried to apply to a new kind of using, this is a kind of, he called a degenerate universe, where he's using the Chern-Simon action and using the symplectic structure, and in this one, Zanelli and collaborator combined the problem of multivalent Hamiltonian and the problem of singularity and dimensional production from the Chern-Simon theory. On the other hand, we have Hordensky. Hordensky also is nonlinear, and therefore the problem is also present there. And in cosmology, there are, I don't know how many, but maybe 1,000 articles about K-essence, and that's what the people call non-canonical kinetic term. Therefore, there are more situations where nobody cares about the Hamiltonian formalism. Yes, we are changing our canonical kinetic term, and we go to the Lagrangian, then the equation of motion, and then we do the cosmology and put the observation, and everything is almost okay. But the Hamiltonian formalism is not well defined. And at the end, when we start to do this problem, we try to see what happened or what is the implication of this nonlinear term and what is the implication of this pathology. And at the end, we finally like this slice in a completely block problem, a completely wide problem without any information, because the problem is complicated for the computation, but the problem is also complicated for the interpretation. We need to see what is the real interpretation when we have multi-value system. What happened, for example, with the thermodynamics? Can we relate these kind of things describing here? If you try to see what is happening here, is quite similar to a diagram of energy when we have a phase transition. Therefore, we try to do, and we are working with this Lagrangian, trying to see what happens if we consider this like a Gauss-Bonnet gas. And we are trying to do the statistical mechanics in this case in order to see what happens with the thermodynamic property. And we want to relate this with this kind of diagram where we can see if we think the Hamiltonian is the energy, here we have a phase transition, but the Hamiltonian is not the energy. Therefore, this interpretation is not correct. But we are trying to do what happened with this kind of a particle, free Gauss-Bonnet particle. But we have a lucky finding, and we found this article about the thermodynamic of space-time and the Einstein equation, and the Einstein equation like an equation of state. This is an article from Jacobson. We can obtain here a kind of the relation between the thermodynamic and gravity. And from the thermodynamic point of view, we can obtain the gravitational equation. And we have the entropy. We are able to obtain our equation of motion. And then we would like to see what happens if we have our equation of motion. We can obtain our principle, our variational principle. We need to try to do the inverse problem of the variational calculus. And this is one of the corners that we are working on this. Then we start to study this kind of thing, the thermodynamic on the horizon. But at the beginning, just from the geometrical point of view, we know one Friedman-Robertson-Walker universe in 4 dimensions, a flat model that is described by the metric, the very well-known metric. And we wrote this very well-known metric in this way. And then we follow the Valerio-Fanagoni procedure, and we can show at the end we can write this metric like a Schwarzschild matrix. And if we have a Schwarzschild matrix, we can define an horizon. But an horizon that is evolving, because here we have a dependence of the time. Therefore, this horizon is evolving, but we have an horizon. And that's the reason why this is called an appearing horizon because it's evolving. It's not exactly the same way when we work in black holes, because this horizon, in the case of black hole, is static. This horizon is evolving. And after that, we will see, we think about the black hole thermodynamics. We know we have all the machinery about black hole thermodynamics, but we need to do something in order to apply this machinery to this case, because we have an horizon. If we have an horizon, we can define temperature, and then we can see what happens with the entropy, and then we can see what happens if we want to write, for example, the equation of state for this metric, for this description, in this case the universe, and we will see what happens with the phase transition. Then we compute the temperature, but now we need to put some surname to our temperature. Now we call Kodama Hayward, because now we are not exactly doing the same compute than Hawking, because now we don't have Killing vector, temporal Killing vector in our metrics. Then we need to define how to levels the time, and we use a different kind of definition. We use the people call Kodama vectors. But then the temperature is given by this expression. This expression at this level is depend only on the metrics. If we change the geometry, the gravity theory, this definition is not changing. This definition is the usual definition for every modified gravity, and just we need exactly the same geometry, and the geometry is the geometry of one Friedman-Robertson-Walker universe. And the other ingredient here is the entropy. We need to introduce the entropy, and here we are using the usual definition. The entropy is a quarter of the area, therefore it's the entropy of Beckett and Hawking, because we are thinking our underlying theory is Einstein gravity theory. Then we have the temperature independent of the theory, but the entropy is not completely independent. The entropy could be dependent of the gravity theory. Then we can write the first law of the thermodynamics, and we can do the comparison with our case, and we put one first law where we need to see here we have a work. This is a work because our universe is in an expansion, and this term is due to the flux of energy around the horizon. And when we do this comparison, we need to do this identification in our variable, the mass, the energy of the black holes, but this also is not the standard one, is the Misner's chart mass here. And when we put our answer is one Friedman-Robertson-Walker cosmology, and we are assuming a perfect fluid, therefore we can moderate in a very easy way this, and we can do the compute. This compute is straightforward. We can show the work in this case is depend of the density, matter, and pressure inside of the universe. And when we use this with the Friedman equation came from the gravity theory, or came from the definition of the entropy. If we were given the conjecture of Jacobson, we can obtain this equation, and with this equation, this is just a changing of this, we can obtain a relation between the pressure, temperature, and volume. Or we can obtain a relation between the temperature and the apparent horizon. And in this case, this is the regular case, Friedman-Robertson-Walker, Einstein gravity, and the equation is very simple. And if you want to see what happened with the critical point, we need to see what happened with the first derivative and the second derivative of the pressure. The first derivative with the apparent horizon, and the second derivative with the apparent horizon. And in this case, it's straightforward to show there are no solutions for this equation. Therefore, there are not phase transition in this case. There are not critical behavior for this kind of description. this allows to obtain our first result. Our first result was to see what happened when we try to unify the first law of thermodynamics in the Gauss-Bonnet gravity. If we change, we obtain the Gauss-Bonnet gravity. And also we try to see what happened when we are working with Einstein-Gauss-Bonnet gravity, and we obtain phase transition, and we obtain different behavior in 5 dimension, 6 dimension. This was our first approximation. The problem was this critical point we couldn't relate it with the maximum minimal solution of our Fourier equation. Therefore, our problem is still open. And here we have the ingredient. The ingredient are when we want to write the equation of state of our system, we need different input. The first input is the gravity theory. If we are considered Einstein-Hilbert, this equation is linear, and therefore we don't have any solution for this for the critical equation. And when we change gravity theory, there are so many papers doing modified gravity. It's possible to find a phase transition, and also there are people that are changing entropy without any principle, without know the gravity theory. We change the entropy. We use Babel, Mitra, or Kaniadakis entropy from different motivation. The entropy is a function of the area, and also we can obtain phase transition. And this is a very well-known area. Everyone has to know how to deal with this, changing gravity theory and obtaining the equation from the entropy and back to the cosmological equation. But this is a dotted line because this way is not still open, because we need to see what happens with the inverse problem of the variational calculus. In our approach, we forget about this branch and we change the matter contents. And until we know this is the first time somebody changed the matter content, and very fast. In this case, we consider Einstein gravity, and we change the matter content. We obtain exactly the same. The machinery is exactly the same machinery. We have an abelian horizon. We define the Kodama height per temperature, and we obtain our cosmological equation. But we put in our case, the matter is described by dark matter, by dark energy. And in this case, we know this parameter in cosmological coincidence. We put in our equations, and we obtain this equation in blue, where now the structure is non-linear, and we hope there are some phase transition. And of course, there are phase transition because we change the structure of the equation of state. Now the equation of state is non-linear, and we need to see how is the relation, and then we need to decide to describe the dark energy in some way. And we use the holographic dark energy, we use the Rafael Busso principle, holographic principle, and when we do that, we can show, for example, in the case when n is equal to 1, we obtain phase transition because the case n equal to 1 is Einstein, regular Einstein Fermat-Robertson Pocket universe. But when we are changing n, we are obtaining phase transition, we obtain a critical pressure, a critical temperature, a critical volume, and we obtain something very nice because in Van der Waals fluid, in Van der Waals theory from condensed matter or real gases or real thermodynamics, there are a universal number, that one, and this number in this case is an upper bound for the real gases, and for our case is the lower bound. And we can see what happened in different kind of holographical models, and this holographical model also will be studied from the gravity side, and we obtain the typical picture for the pressure and volume for the Van der Waals fluid, and we obtain our phase transition for that in this case are shown by the reduced free energy. And after that, we apply another model, a kind of Granda-Olivero model, or maybe audience of cutoff. I don't know exactly who was the first guy. I know by audience that this was an audience of cutoff, but I'm not sure. And in this case, also, we obtain a modified equation of the state, and we obtain phase transition. And this is just running. We change the entropy. Now we fix the matter, but we don't know the gravity theory. Just we know the entropy. With this entropy, using the first unified law and the Clausius relation between flux energy, temperature, and entropy, we can obtain this equation, and this now are our Friedman equation, a little bit more complicated. And here is the formal way when we can define the temperature and the appearance horizon. This is called traverse surface. This is a very formal way to see this. And this depends only on the geometry. This is the chain of the energy, this is the chain of the entropy, and this is the chain, this is the award because the universe is in expansion. And also here we have, of course, a modification, and we obtain our equation of state. And of course, here it will be possible to obtain a solution of the critical condition, but these equations are transcendental, therefore we do an approximation, and this approximation is plotted here. It's very close to the exact equation. The black line is the exact solution, and the other, the blue line is the second order, and the red line is the first order. And in any case, we obtain phase transition, and when we are doing this Kaniadaki parameters go to zero, we obtain the Friedman-Rosen-Walker, and here we don't have any phase transition. And here, the open ideas. Therefore, our original problem is still a number problem. We need to back, maybe with a more formal way to describe what happened with the Hamiltonian, multivalue Hamiltonian and phase transition. We still don't have the connection. We hope where we have the solution of the Cubic equation, where our point of the phase transition, but we are not able to do that yet. And the other idea is to see what happens when we are using more general or more correction of the Einstein-Hilbert Lagrangian that have exactly the same pathological behavior. Maybe we need to see again another problem with a new interpolation. For example, for Chern-Simons gravity, here I have Laplace because I am thinking in a general way. If we have even dimension or we have odd dimension, we will have Chern-Simons or Gauss-Bonnet or more correction about it. And also, we discovered that we have three possibilities, but this is a very well-known working area. Manos showed 100 at least modified gravity. And also there are many papers doing that. The other example is to modify the entropy, but here when we modify the entropy, we don't have the fundamental principle. And at the end, we are seeing this Kaniadaki parameters could be a running Kaniadaki parameters. Therefore, we need to be more careful and put the dependence of the energy. At the end, our proposal was modify matter content in order to obtain phase transition. And now we are working, trying to see what happens when we have a interaction between that matter and that energy in order to try to see what happens with the observational data. And our new is to see how we can obtain the general, when we consider generalized entropy. That means we can have f of h equation of motion, and we will try to do the way around and try to see what is the general principle, the general variation of principle in this case. And that's all. Thank you.
Questions?
indeed. My question is simple that, you know, I really like this stuff. Some other people ask us the following. Are we considering equilibrium thermodynamics? Because, yeah, I mean, depending on the Hawking temperature, in the last one that you showed, there is also R dot. Yeah, there. So this is one question, and their argument is the following, that if you take your equation and you calculate the temperature of the horizon, you find 10 to the minus 15 or something. And some people claim that, but if this is the temperature of the horizon, and inside the universe we have the C and B temperature, then you should definitely have a flow, so you're not in equilibrium. So what is your comment?
In the case of interactive fluid, we are trying to deal with that. And our approach is we need to move forward. We need to see what happens outside the equilibrium, and we need to see what happens when we are generating entropy. And we need to try to see what is the real interpretation when we are doing thermodynamics on the cosmological horizon. Because we don't have Hawking radiation, we need to see what is happening in order to see the production of the entropy. Yes, this is a huge problem.
Hello, thank you for the nice talk. I wanted to ask about the problem of the multi-valued Hamiltonian. So you show a reference, and I understand that one of the solutions is to define like generalized coordinates, let's say, and then you will have let's say a system with only some generalized canonical momentum. Yeah, that one. But they say like it's not always possible to find these coordinates for any.
You can find this coordinate and you can find this Hamiltonian, but the problem is I don't have the canonical transformation in order to show these two Hamiltonian are equivalent.
Okay.
So these two Hamiltonians describe exactly the same system.
Yeah, exactly. And for instance, in the example of Teitelbaum and Henault, is like they have 3 different values for the momenta, so 3 different Hamiltonians. Okay, so the solution to that problem will be to define some different coordinates that include.
One solution.
Okay.
And this is the solution that apply here around.
Okay.
And there are other people working just in multivalued Hamiltonian. This is the friend of Eduardo, Ulrich, that he worked in Florida University. But he applied for different kind of system that present this kind of property, the multivalued Hamiltonian.
Okay.
Here the problem is with 2 different approaches. One generalizing the Legendrian transformation, we can obtain 1 Hamiltonian.
Mm-hmm.
Exactly the same previous problem.
Mm-hmm.
And Abraham for the same. Applying this kind of a modified Dirac program, they obtain another Hamiltonian.
Mm-hmm.
And I hope, because we know that from the classical mechanics, these 2 Hamiltonian will be connected by canonical transformation. And this is not certified.
Okay.
Therefore, the problem is reduced, but the problem is still there.
Okay. But like you said, like some systems don't have a well-defined Hamiltonian formulation. But what if they just don't apply? I mean, like the Dirac program doesn't apply to these Lagrangians, or for instance, like only if you take into account the Lagrangian and the Lagrangian equations of motion, is there like any problem there, or is just when you go to try to find some Hamiltonian that then you're or quantization?
Also, in the Lagrangian there could be some problem because we have nonlinear terms.
Mm-hmm.
But maybe this kind of behavior was shown by Natalie Leruel and Fariña applying for cosmology.
Mm-hmm.
Just from the Lagrangian point of view, they wrote the equation of motion and then applied the dynamical system machinery in order to see what happened in the phase space in the configuration space, and there are some regions of catastrophe.
Mm-hmm.
Because there are bifurcation and other things that came from the nonlinear view.
Yeah, exactly. So in that sense, isn't like a problem of the theory itself instead of the yeah. Okay.
Then this is the most economical way to write the gravity.
Yeah, and maybe one short question also. Like, if you have different Hamiltonians and you do, let's say, the full Hamiltonian formulation for each one of them, do you obtain the same degrees of freedom, or are they different?
I don't know. I don't know.
Is there like
I don't see the count in this case.
Okay.
I'm not sure.
Because there are other Hamiltonian problems in these FOT theories where you have, like, I mean, it's not multivalued, but then you have the Hessian has rank, variable rank, and you have.
I have exactly the same concern. My biggest problem is that one. When people apply to Kaysen's model with non-canonical kinetic term, they are introducing this kind of problem in the theory. But nobody care about this. Therefore, there are differences. So they are doing the counting of the degree of freedom. There are different behavior. And this article is exactly showing this.
Yeah. Interesting. Thank you.
I have a question. I remember the papers of by Estelle of the late 70s. He also found other classes of models goes free. Have you looked into them? Do they also have the convexity problem of the Lagrangian? Because Estelle has one or two papers in the late 70s, considering that problem, and he found also other classes of alpha, beta, gamma parameters with other theories that also are ghost free. And some of them has also spin 1 particles. But have you studied it?
I didn't see the paper, but I see so the equation of motion and the second order in this case?
Yes.
Yes?
Yes.
Another combination from the Gauss model.
He looks exactly for that, well-behaved theories free of pathologies.
Nice. I will see the
Anybody else has a question?
Hello, thank you for the talk. I was wondering if the Hamiltonian is multi-valued. Does it mean that the phase space has non-trivial topology? You cannot find a canonical transformation that takes you from one Hamiltonian to the other because it doesn't exist, basically? Or is it you haven't found the coordinates yet? Okay, interesting. And the other question that is maybe more basic, why do you need the Hamiltonian formulation? Is it because you want to define a mass content, or I don't know? Can't you? Is it because you want to quantize? Can you use the path integral formalism?
Whatever what do you want to do, you need a consistent. The Hamiltonian and the Lagrangian must be consistent, because in other case, the canonical formulation has some mistakes. Just for motivation, my principal concern is about, as said recently, about these guys. When they apply the non-canonical kinetic term with a function of the velocity in front of the regular kinetic term, there appears some solution that has some critical dynamical system, and they have some critical regions, and these regions are not connected with anything. Then, and also we have a sound velocity instability. Therefore, my guess is this kind of instability are related with the Hamiltonian problems. That is my guess in this case. But I certainly, you can move forward with the Hamiltonian formulation. You can try to obtain main results. For example, if you are seeing the black holes, the Gauss-Bonnet black hole, you can do anything, whatever you want, without any trouble. But in this case, it's not free. For everyone working in non-canonical kinetic term, this kind of doesn't exist. The Hamiltonian stability. That's my main concern.
Okay, thank you.
Anybody else? Okay, so we thank the speaker again. The next, Milko Estrada. You changed? Yes. Okay, go ahead.
Sí, lo que pasa es que me habló ayer, me van a cambiar. Sí, por favor. Sí, sí. Okay.
Está bien, ¿no? Fíjate si funciona para avanzar eso. Okay, so our next talk will be, our next speaker is Jenly Leon, and the title of his talk is The Dynamics of Scalar Field Kingdom Cosmological Models.
For the third time, I will speak about an idea that I visit time to time in the last 20 years, which is a non-conventional kinetic term. This is a work we did with in the House University, and it's supported by a fantasy grant. ¿Cómo? Eso. So this is the outline of the talk. I will present the model in which we have two scalar fields, which are open in the kinetic terms. I will proceed with a dynamical system formulation, and we will explore the cosmological implications. We will explore also the effect of considering the spatial pressure in the models, and schedule something about the perturbation analysis, and then we conclude. This is a theory in which we have two scalar fields. It is supposed that, what we would like to do is to investigate the early time inflation within these models, and also about the late time cosmic acceleration. The Clinton model considers two scalar fields, one which is a conventional scalar field with a standard kinetic term, and the other one is a phantom scalar field with a negative kinetic term. And in this case, when we examine the model, we can see that we don't have any Gaussian instabilities, because in this process, the quintessence field will dominate. And so with the evolution, this field is a problem at the beginning. So a way can be solved. This is a Lagrangian. Here, phi is the quintessence field, C psi is the phantom field. This is a coupling between the C and the phi and the C, and we consider the simple exponential potential. When we include this metric, the Freeman-Rosen-Walker metric, first we will examine the flat case, and after that we will see the imprint of the curvature in the inflationary solutions. These are the equation that comes from variation of that Lagrangian. this is the Freeman equation for the flat case. This is a Faraday equation. Here H is the Hubble parameter. And these are the generalized plane-Gordon equations. Observe that the second one, 6, is quite different from the standard. And here we see that there is a coupling between the kinetic terms explicitly in the equations. And for simplicity, we consider the exponential potential. We have here a problem. If we examine the Freeman equation, we see that this term here is negative. So if we use the standard procedures, we will have a non-compact phase space. What we do is to consider a different normalization, and it's this one. We use the linear density of the color field as the term to construct the dimensions variables. And here we see that in this choice, our phase space is a two spheres, two circles. So it's compact phase space. And using the new variables and defining a new time, doing the standard procedure of the dynamical system, we found this nice two-dimensional system. The idea of this model is because of the definition we use, it is possible to have a crossing by the value h equals 0. So we can have a natural crossing by 0. This is not allowed in the standard dynamical system variables. We analyze the equilibrium points. These are the ones related to quintessence. This is a kind of scaling solution. We obtained and found that these four solutions represent different inflationary phases in our model. The idea of the procedures we use is to employ dynamical system techniques to find a region in the parameter space. Sometimes this region in the parameter space, one found in the theoretical analysis, can be used as prior if we want to estimate the parameters using bar or supernovae, etc. So in complement, these methods are very nice to start theories. These are the eigenvalues. I will not discuss this in front. When we analyze all the region in parameter space, we found that this solution allows for multiple inflationary phases in this model too. But there are different combinations because we can have a phantom, quintessence, phantom, quintessence, and there is a rich nature here. And there is a transition between quintessence and phantom domination. It's also a way that we have a lifetime dominion by quintessence. The parameters we use to check if the solution is accelerated inflationary, for us is the same. The difference is in the epoch, if we are in the early universe, it is related with the primordial inflation, and in the late time, it could be related to the dark energy evolution. In the analysis, we consider the acceleration parameter, and we discuss some of the dynamics. We consider that there are solutions related with inflation. Some of the points are on the boundary, like E, but others are at the interior. For example, in the point H, both fields contribute to inflation, and this, while the point A is a single free inflation that all knows. Importantly, when we examine the evolution of H, these are some support types, and this is the important plot I want to show. Here we have a solution. The green one, I don't know if you see the green solution. Sorry, lost. This solution is a solution that is related to a bouncing cosmology. In this case, the solution passes through the value equals 0, and then it grows from negative h to positive, and then it ends at a quintessence dominant point. If we go to the diagrams, we see that our system emits bouncing solutions. It avoids also cosmological singularities, and this is a representation of the log of h, and it corresponds to the bouncing solution. And asymptotically, we found that this branch is approximated by this power law solution, and this power law solution provides inflation. After that, we extend the analysis by including curvature. When we add curvature to the Freeman-Lemaitre-Rose-Walker metric, we have a modification, and then the idea is to examine how the curvature affects the stability and dynamics. This is the model. It is the original one, but now we have a new term, which is the last, I think, and all those terms with k. K is minus or plus 1. We, as usual, define a similar fractional curvature density. It is in 23. Here we normalize with the kinetic energy, with the energy density of the scalar field, remember that. And then this is the Freeman-Rose-Walker can be written in this way. By definition, psi is positive. Here it could be positive or negative. In a following analysis, we use compact variables, but here it is not necessary, because what I want to do is just to see the impact of the curvature on some specific points, the ones that correspond to inflationary solutions. But the extension was done the last year. This is a result from 2022, the one I'm describing now. This is our system. It is a three-dimensional one, and then we focus only on the solutions A, F, G, and H, this type of solutions, that in the flat case they are inflationary. And again, we calculate here the acceleration parameter, it is equation 28. And when we evaluate this at the fixed points, we found that they correspond to acceleration. And yes, in principle, the stability of the points essentially is not changed. The only thing that happens is that the parameter space is reduced, because it appears a more restrictive constraint. In the case of the flat solutions, lambda squared could be less than 6. This is the condition for having a inflationary solution. And here is only a reduction of the parameter space, in the sense that some of the points appears in the dynamics and they change the stability of the whole system. This is a standard in dynamical systems. But still, the curvature doesn't prevent the possibility of having two inflationary epochs, as in the flat case. So there is not a crucial impact of the curvature are stable against conventional perturbations. Finally, to prove that the model is consistent, we consider here linear perturbations, linear cosmological perturbations. We perturb the scalar field and the metric around the Freeman-Rosen background, and then we obtain the equation of motion for the perturbation, and we examine this equation. We use a Newton and Gauge eccentricity to introduce case invariant variables. I mean, we use define invariant Gauge variables. And here is the procedure. Let me briefly discuss the procedure. This is the perturbation we consider of the Freeman-Rosen Walker metric. We follow a reference. This reference is well suited when we have multiple scalar fields. We expand the scalar field in this way. And then, because we are working in an internal phase space that is a chiral space, we also perturb the metric around the knot solution. And then we use the perturb Einstein equations. After that, we go to we do a separation that is possible because of the internal symmetry in the phase space. And after all, we can have this evolution from the perturbation equations. Theta and H and sigma are well-defined quantities. And in these quantities, we go to the Fourier space. Then this is the evolution and the Fourier space. And what I will show now is that we will use the background dynamics for which we define a dynamical system, but we include on top of this equation the perturbation, the equation for the cosmological perturbations for this scalar we introduced. And the idea is to examine the stability of that system as a full system, not evaluating this fixed point at the perturbation equation and then examine the perturbation equation as a different system. What we work is in an extended phase space. This phase space has the background dynamics, and the evolution of the perturbation can be written in this way. This is a standard equation system. And this is the point. Instead to evaluate 61 and 62 at some fixed points and then examine the evolution of perturbation, we consider extended phase space. This is the extended phase space. It has a structure of the product space, at which we have background quantities and their evolution, and also perturbation quantities and their evolution. And we examine inside the Hubble horizon and above the Hubble horizon. For that, we consider this variable set that is related to one of the quantities that appears in the evolution equations. And this is the full system in which we incorporated the background dynamics and also the perturbation, the dynamics of the cosmological perturbations. This is depending on the compact phase space, and then we calculate all the fixed points. For this point, we have 2 or 3. I mean, for the background points, we define for the A, the F, E, H, etc. We have up to 3 families of points where we go to the extended phase space. And some of these cosmological perturbations are stable, other one are stable, and then we investigate all the phase space, all the parameter space, and obtain which solution are also stable when we consider the perturbation. That's all. Then we classify all the source of the phase space. Again, this is to produce some region on the parameter space. Also, we discuss all the things. Then we consider some projection of the evolution of the system in the extended phase space. And then it is consistent with the background analysis we did. That's all. We provide a comprehensive dynamical system analysis in the quantum model. We identify conditions in this model for two inflationary epochs. We also prove that the inflationary solutions are stable against population perturbation. Also, we explore bouncing cosmology within this model and study linear perturbation. The problem is that the bounce cannot be seen if we use the standard Haber normalized variable, because we know that at the bounce the base goes to zero, and then the original dynamic analysis that it was created in the 60s can explode in these kind of models. And for that reason, it is important to define when the variables to avoid blowups in the evolution equation, etc. Okay, we already considered another configuration in this internal phase space, but we can investigate more general potential than the exponential one or beyond. And of course, we have a theoretical value of phase as a function of set the redshift. We can proceed with all the machinery to test the models against those equations. These are some references. The first time we worked in this model, it was like 20 years with 2 sigma, maybe in the 2006. And we use some important papers and books to learn a little bit on the theory of cosmological perturbations. And the procedure we use for the chiral scalar field is the method by Chevron. Okay. And there are other important works by Arco and Mugla, also this seminal work with Manos here. It was the first, one of the first, I don't know if the first, no, I think not, because there are several before, but we systematically use this idea of use extended space, considering the background equation, also with the perturbation. And the last one is the vector with this electron space. Thank you.
Questions?
Henley, very nice talk. What is the reason that appears a bouncing cosmology? Who is the guilty guy?
Okay. It appears. It appears. We are interested in solutions that have the evolution of the scale factor and that it goes to a minimal value and then start evolving again. Those were because mathematical interest. And what is nice here is that without, if we use the usual or the standard normalization, we cannot see this bouncing solution. So this leads another question. Maybe is it the bound solution an artifact of the variables we chosen? No, there are bound solutions. And we discovered in this scenario because we use the correct variables to get there. And it was one of the, but the main issue, the main interest was in the inflationary solution. That's the main point of the.
Here is the bouncing solution was there.
Yes, it's there. But if you use a variable that, for example, you remember that in typical dynamical system, people divide by age. They use age normalization. These variables are not useful to get the bounce because age will be 0 at the bounce. And for that reason, the solution are there, and it's not a discovery because in paper by Duta, they found before, and also Manos, the bouncing solution in this Quinton scenario. Okay.
Anybody else?
Thank you for the nice talk. I have a couple of questions similar to the Joel. In the plot you show the direction field. Which is the point of the bouncing?
In this plot,
No, en el where in the direction flow. This one.
the line will cross by 0.
Ah, okay, yeah, okay.
The green line.
Okay, and the point E is the basically the inflationary regime, the zeta.
E is a inflationary regime and also F. But F is a inflationary regime that is a source. So it is correlated with the past inflation. So there is a kind of model that goes from an early inflationary phase to the late time acceleration phase. But even though it passed through this point, at least there is a bounce.
But in the F point is of the universe which is going to collapse or what?
Yes, the point goes to a minimal value of phase.
Yeah.
Here is 1. Remember that is a log A.
Mhm.
Here is 1, the A1.
The one.
It is put in the way that the time for the bounce is late, but
The one.
because
Choose. Then you model finish in the inflationary regime.
the model then finish after the bounce.
Okay.
It goes with a power law expansion for the edge that provides accelerated.
Okay. So, but this is inflation. This don't have actual acceleration. I mean, the dark energy problem. I mean.
The rate the inflationary phase is that element.
Okay. And the other question is, in this case, you have to maybe include another field to make reheating or something like that, because your potential are not don't have a minimum. Are you thinking about that? See? Final question: when you show the perturbation and for a different equilibrium point, which is the result for the case of the F point of the zeta point, the inflationary point? What you can conclude of your perturbation? E. You have any comment? No?
Look, in this point, the cosmological perturbation goes to 0. Here, it goes to 0. It means that the perturbation decays, and this is stable for a run of solution, but also there is another point at which the perturbation doesn't decay. And what we did is to to put the condition for the stability in the whole phase space, within the background times the perturbation. And let's look at the A. Here is the normal A with the zero perturbation delta is a sink for this regime. And when lambda is less than the square root of 2 in modules, and this condition is considered 2, there is a condition for inflationary phase. When the lambda is between square root 6 in modules, between square root, between the lambda between the square root 2 and 6, it is an accelerated quintessence, but it has not inflationary behavior. And this is the information. For investigate if the cosmological perturbation are also stable at the point, we need to see the phase space, the parameter space. And for that condition, yes, the perturbation decays. And also for the other one, no, it is also decaying the perturbation, but not to zero, but to a constant value. It is stable also for this region. We can see that it's quite different because it's the complementary region. So in any case, we also always will have an A point that is stable. Because in this regime is this one, but in the other regime is the other one. We can see that these are complementary conditions in the lambda. Okay, and this one is important to have an inflationary phase. And here are the points. Here, zeta is the vertical edge. Zeta 0 is inside the horizon. Zeta 1 is outside. So what that means is that the evolution is that the solution go inside the Hubble horizon. I don't know the physical application of that, but this solution goes inside the Hubble horizon.
Okay, thank you.
So at the background level, we want a saddle point that is matter dominated,
yes,
and a stable point that is that kind of dominated at the background. Now the perturbations, this perturbation variable, we want at the matter region to be increasing, so we want constant, but today perturbations are constant, so we want 0. So we want a stable point in the end, that the perturbation has it. So did you find these points? You found this E minus, which
are those,
exactly. So they have this perturbation variable is 0 in the stable point.
In the A's, but in the A's asterisk.
Exactly. So we need to be 0, exactly. So this is the important thing that we will discuss. So the last one is the good point.
Yes. Okay. Thank you, my apologies.
Okay, we thank the speaker again. And now we can go to the coffee break.
Aló, aló. Ay. Joaquín Robledo. Le envié ese. Ese. Oh, no llegó.
Pero espera que te presento.
Aló, aló. Aló, aló.
Okay. Okay, please sit down. So our next speaker is Joaquín Robledo from Universidad de Tarapacá, and he will talk about nonlinear scalarization or Schwarzschild black holes in scalar torsion teleparallel gravity.
First of all, can you hear me? Yeah. First of all, thank you for the organization, for the invitation. I'm going to talk about my paper with the professors Pablo González, Lefteris Papatanopoulos, and Jerko Vázquez. I'm going to start.
So this is the outline. I'm going to talk about the motivation of the work, a really fast context of teleparallel equivalent of general relativity, the model, the solutions, the thermodynamic analysis. So, well, like 2 years ago, Daniela Doneva and Stoiko Yahatzagdayev make this paper about a new mechanism of scalarization of black holes. Well, they did it in the context of a scalar Gauss-Bonnet theory, and my question was, this will work in teleparallel gravity? This is the motivation. So we try to do this and works. So a really fast context of general teleparallel gravity. We use the Weissenberg connection instead Levi-Civita connection. So in this frame, we have only torsion and not and vanishing curvature. So, and the equation of motion are equivalent to the general relativity because there are equivalence between the scalar of torsion and the rich scalar. So plus a boundary term. So how you see before, the scalar of torsion is given by the contraction of the torsion and a superpotential. Well, the superpotential is given this way in terms of the torsion. Well, it's defined in terms of the contortion. That is the difference between the Levi-Civita and Weissenberg connection. So the also is related to the torsion. And this is the action of the teleparallel equivalent of general relativity. Well, this is the scalar of torsion, the matter Lagrangian, the determinant, and the constant. You know? So the equation are that. This is as I've said before, is are the same. This field equation are exactly the same of general relativity for every geometry choice. Now I'm going to show the model of nonlinear scalarization. Basically, this is the model, and for it's a scalar torsion model, in that the coupling function has to meet the following condition for the existence of the nonlinear scalarized black holes. So these two conditions are very important because the first condition guarantees that the Schwarzschild solution is solution of the black hole of the field's equation, and the second is the most important, is that with this condition has no tachyonic instability in this theory. And this coupling function is maybe an infinity coupling function that follow these conditions. So we choose the simplest, and we'll start with that. So by interaction, we get this equation, the field equation, and the Klein-Gordon equation. We can see if the scalar field is 0, we can recover a teleparallel equivalent of general relativity. And to found the equation, this is a very hard. These are very hard equations to solve. So we first assume a spherical symmetry, and we consider this tetrad. And this tetrad gives the standard metric form of an object with a static and symmetrical spheric. So, well, using the tetrads, we get these 4 equations: the temporal equation, the radial, the angular equation, and the Klein-Gordon equation. Well, to find solutions, we consider solve the system numerically because it's very hard to to make it analytical. And I don't know if we really have an analytical solution, maybe. So we consider this new bounded radial coordinate to help us to solve the system. So we redefine the metric functions and the scalar field. The equation was solved using the shooting method. And well, for zeta equals 0, we are at the event horizon. At zeta equals to 1, get to spatial infinity. So considering this, we get the expansion for the near the event horizon and near the spatial infinity. These are the expansion. Well, we get some parameters that give the expansion and the field equations. For example, this, you can see that all the parameters are determined by the eta parameter, by the AH, BH, VH, and at the horizon, at the infinity, we get all the other parameters are defined in terms of the A0, B0, and phi infinity. So we are searching for the asymptotically flat solutions. So we need some boundary conditions that are the following. So H0 needs to be equal to 1, and B0 needs to be equal to 1 also. And we need to that these conditions follow. So only need that the field needs to be regular at zeta equal 1. So the solutions are determined by the 5 parameters here: eta, H1, AH, VH, phi infinity, and phi1. So we found for a fixed eta that a specific value of these parameters allows a bounded scalar solution. And also found that for a small value of eta, only 3-node solution can exist, but as eta grows, multiple solutions with different or even the same number of nodes can appear. In the paper, we did for 3 values of eta, and only here I'm going to show about one of the solutions. I'm going to show some graphics, some figures to compare with the Schwarzschild solution. It's the main for show the deviation of the Schwarzschild solution. So we can see here for a solution of the branch for 0 nodes is very similar to Schwarzschild. We get that this term is very similar to Schwarzschild, and the V1, that is the term related to the mass of the black hole, to ADM mass of the black hole, is near 0, so it's very similar to Schwarzschild. So, well, the graphics are not so big, so I'm going to explain that. The cyan line is the first branch of the scalarity solution, and we can see it's very similar, as mentioned before. It's very similar to Schwarzschild, as for the metric functions A and B, and the red and blue line are the second and the third branch of the solutions for eta equal 2 are a little far of the Schwarzschild solution. Here we have the scalar field. We can see that the cyan line for the first range is have no nodes, and the second and third branch have nodes, have 1 node each one. And here in the right side, we plot the scalar torsion, and we can see this have a regular behavior. It's regular at near to the horizon and 0 from on the infinity. So we did a thermodynamic analysis, and we did by two methods. The first is the Padmanabhan method, in which we take the equation, we evaluate in the horizon and give the equations, and we rewrite or manipulate to construct the first law of thermodynamics. So we get the black hole mass and the entropy given by that way. And also we did with the Wald formalism and construct the nether charge, where when we vary in the equation, we get a boundary term that we identify as symplectic potential. After that, we construct a nether prepotential, the nether charge, and so on. And we get this expression. We can see the entropy is equal, but the ADM mass is different from the mass of the other method. This difference is in principle because when we put the numbers are equally the same. It's very interesting, but for the safest, we take the safe option and we plot the other quantities and compute the other quantities in terms of the ADM mass found with the Wald formalism. So we get here we plot the ADM mass and the thermodynamic and the entropy in terms of the ADM mass, and we found that the scalaristic black holes are always entropically preferred over the Schwarzschild solution. So we always get bigger entropy. After that, we study the first and second order phase transitions, and we get that the black holes are the black holes are metastable and don't exhibit any change of sign of the head capacity or the or strange behavior at the free energy. So don't have first or second order phase transitions. That's basically all what we do. So we consider this new mechanism of the scalarization of black holes in the context of teleparallel gravity, and also we found that the scalarized solutions are metastable and don't exhibit phase transitions. And I found the more important thing I think is that scalarized black holes are always preferred over the Schwarzschild solution, thermodynamically and entropically preferred. So that's all. Thank you so much.
Questions?
Thank you, Joaquin. Maybe it's a simple question, but in the model of nonlinear scalarization, do you have a tetrad?
Yeah.
So the question is, why do you have an imaginary number in the tetrad for the because it satisfies the condition or what?
Well, in teleparallel gravity we have a problem with the real tetrads. So we firstly try with the real tetrads that have a physical meaning that gives the standard metric, but when we do the expansion, we found that they have problems at the horizon. We get B equals to 0, A equal to 0. And so basically this is that was the reason to consider this imaginary tetrad. And I believe that Alex Golovnev and Professor Maria Jose, they did a paper talking about this. This have in the horizon, the vector field don't have a smooth transition between the inside and outside the horizon. the vector have the space-like vector field doesn't smooth doesn't transit. Well, sorry. Well, I have the answer that I did. Can you understand? My English is not so good. Sorry.
Any other question?
A comment about this imaginary complex tetrad is that I guess probably in this case it's the same, but it has real torsion scalar and real equations of motion, right?
Yeah. But in this case, only get real equation of motion.
And the torsion scalar?
Pardon? No, the torsion scalar have a real behavior, so a non-strange behavior.
Yeah, so they don't have imaginary part. In
No.
that sense, like there was a debate in this, complex tetrads, and if the observable things give like real values, then maybe it's or it's not a problem. I think the problem is if you want to perturb this complex tetrad, because you need like double, 2 times more the set of perturbations, because you also have to perturb the imaginary part.
Yeah, we also have this question if maybe, I don't know, maybe this happened because we are considering a diagonal metric. If we consider a non-diagonal metric with a real tetrad will work, or I don't know if you understand my question.
Like you mean if you consider
a non-diagonal metric, but a real tetrad, this will work?
You will have to see.
Yeah, it's because I also bothers me that the complex tetrad.
Yeah, actually that's a good idea. I'm not sure if people have done it because they like diagonal metrics.
Yeah.
Yeah, it's a very good idea.
Anyone else?
Maybe not thank you very much for the presentation. Maybe not a question for the speaker only, but for you both. Why you have to perturbate the tetrad in real and imaginary parts, and not only the imaginary parts in the imaginary variables, and the real part in the real variables. And that's it.
If the tetrad were only real, then you will have like 16. Let's say you will have to perturb in the most general part 16 with 16 real perturbation functions. If you have, but this, if you have like imaginary functions, then you need the real perturbations will not perturb the imaginary part. You need an additional set. Yes, but I think it's like in the general formalism, it's like you write like the tetrad plus is equals background plus perturbation, and then this background is like real and imaginary. I mean, probably if the number of perturbations will be the same, let's say, I don't know, 5 for the imaginary part and other 11 for the real, and then you will not have more perturbations, probably will work, but it will be like a particular case and not the most general perturbation analysis. But probably could be some sort of patch.
I haven't listened about the Weissenberg gauge. You need to this gauge for some reason, or is because you want to make something? Can you explain me a bit, short?
The motivation of the work, you mean, or no?
Yeah.
Because the last year I started with studying the teleparallel equivalent of general relativity, and I like black holes. I want to study the black holes in this theory. I found these problems of the tetrads and other things. Also, we try due to spontaneous scalarization is extremely hard. I don't know why. We have some problems with the real and the imaginary tetrads, so we try to do something, and we found this new mechanism to scalarization, so we try and it works. But also, I like to, in the future work, do the dynamical analysis of the system, because only this is the thermodynamic analysis. But yeah, and also I would like analyze some other black holes and test this idea that says to the Professor Maria Jose. So basically, that is the motivation of this work.
Okay, thank you.
Anyone else? So we thank the speaker again. Okay. Our next speaker is. No way. He doesn't like me. Okay, our next speaker is Francisco Plaza from the Observatory of La Plata, and he will talk about testing an alternative cosmological model with observational data.
Okay, good morning. I would like to express my sincere gratitude to the organization for providing me the opportunity to present this talk, and for all the assistance that they provided me in order to be present in this Congress. In this opportunity, I will present an alternative cosmological model that employs a modified theory of gravity instead the general relativity. And let's begin then by discussing the motivations of this proposal. How we all know, the standard cosmological model includes a late evolutionary state with an accelerated expansion through the discovery of it through measurements of type 1a supernovae. So for the model to be able to explain the accelerated expansion of the universe, included the cosmological constant among high hypotheses. However, we don't know the physical reference of the cosmological constant. We don't understand the mechanisms and the physics behind this accelerated expansion. If we analyze the mathematics of the standard model, the mathematics of the general relativity, here we have the Einstein-Hilbert action with cosmological constant, from which the Einstein fields equation are derived, and we don't know whether the term of the cosmological constant belongs, half left side, as part of geometry and dynamics of spacetime, or to the right side as part of the energy momentum tensor as new matter. So following this analysis, several proposals emerge. There are dark energy models that include new species in the energy momentum tensor. There are background energy models that include the background energy of the quantum fields of the standard model of particles. And we believe that this is a good proposal attempt to explain the accelerated expansion through dynamics as geometry of space-time itself. Following these ideas, scientists like Starobinsky introduced and proposed the so-called F of R theories. And if we analyze the mathematics in this context, we have a generalized theory action, a generalized action with an F of R function that is a function of the rich scalar from which the modified fields equations are derived. And we see that in this context it's not possible to interpret some of these terms as part of the energy momentum tensor because they are a function of the rich scalar, clearly part of the geometry of the space-time. And we have here the modified Friedman equations that we need to solve to model universes in this context. Now we must choose the F of R function, the specific function that we will use in this study. And this function must meet a series of requirements, such as describing a good cosmology and successfully passing all solar system tests and so on. And one function that meets all the mentioned requirements is the function proposed by Starobinsky, that has the following expression. We see that is the Einstein-Hilbert action with a deviation that depends on this free parameter B that we call the distortion parameter, because this quantifies the difference between general relativity and the F of R theory. When B is 0, we recover general relativity. These characteristics allow us to employ a series expansion around the standard model of cosmology for very small value for B. When B is in this range of B, we employ the series expansion, and for higher value, for 0.5, we solve the full modified Friedman equations. So we analytically study the model. We execute a Markov chain Monte Carlo method. We include these uniform priors, and we include a Gaussian prior for the absolute magnitude of the supernovae, with the objective to this parameter to be consistent with the astrophysics of the supernovae, proposed by Camarena and Marra. And the data, the cosmological data that we include in the study are type 1a supernovae from Pantheon and Pantheon Plus compilation. We include 20 data points from baryon acoustic oscillations, include 32 data points from cosmic chronometers, and more than 2,000 data points of this new interesting data, the nuclei of active galaxy, the AGNs. And to begin, we execute an MCNC method for the lambda CDN model, and we study the impact of the Gaussian prior of Camarena and Marra in the results, and we see that including the Gaussian prior in red drastically changed the results. So in the future, maybe we can employ other kinds of marginalization, maybe based in other calibration method to study the impact of it. Now the results for the Starobinsky model, we obtain first we execute the MCMC, included the Pantheon compilation and the rest of the data. In this case, we obtain a very close to 0 value for B, which indicates that the behavior of this model is very similar to lambda CDM model. The model that best fit the data is practically lambda CDM. We obtain standard value for the rest of the data. It's a viable model, but it's very similar to the standard. Here we have the results in a table format. The colors correspond to the ones in the corner plot. And the situation changes when we include the Pantheon Plus compilation. In this case, we obtain a very different value to 0 for B. And we obtain an inconsistency at 1 or 2 sigma with lambda CDM model, depending of the case. In the most complete adjustment, we obtain 1 sigma inconsistent with lambda CDM and standard values for the other parameters, and Hubble parameter around the 69, 70. And here we compare our results with similar works. For example, this work of Ravi obtained to a higher value for B. And it's interesting, this work of Kumar, because they include the Pantheon Plus compilation. However, they obtain a very close to 0 value for B, but we see that they employ the series expansion for all cases of B, and we think that they could produce a small value for B. To conclude, we execute an MCNC method with the objective to analyze if the higher value for B is caused by the inclusion of the Gaussian prior or by the inclusion of the Pantheon Plus compilation. And we see that when we exclude the Gaussian prior, we obtain an even higher value for B. So it's clear that this higher value for B is caused by the Pantheon Plus compilation. So we will conclude here, and I leave you with a summary and some conclusions. Thank you very much.
Questions?
Very good. So I have a question that in the end, okay, after you perform the statistical efficiency, in order to analyze the statistical efficiency and accuracy, you need to perform the information criteria. I mean, because you did this model and it's very in agreement with the data, but in order to compare with lambda CDM, you need to take into account, for instance, the archaic information criteria or in order to compare which model is better. So my question is, have you checked that? I mean, in the end of the day, whether Starobinsky behaves better than lambda CDM?
Do you refer to the Bayesian?
Yes.
No, yet no. I want to do this.
More questions?
Nice talk, Francis. I have a question. You first use Pantheon, then Pantheon Plus. My question is with Pantheon Plus, with the big difference is because Pantheon Plus has a lot of very low redshift data. You use it because most of the time someone
we exclude in the first the first data they choose and include the marginalization that is very similar.
Okay,
and
but
now
you cut
we are including the shoes data.
Okay, the shoes below 0.01.
It's the same. The result is the same.
Okay.
Let me clarify that the Camarena and Marrero prior has the same information of the Cepheids. It was built before the collaboration but public this data. So it's the same. To the same. This is the reason for the 72 that he's getting. Anyone else? I have a question. What is the effect of the AGN data? Are they more constraining than the other data or not?
Yes, a little bit, yes. This data is a higher value for the redshift.
Yes, they are high redshift.
So the effect of the cosmological constant in this redshift is less the dominant of the cosmological constant is for zeta equal to 1 and 2. So this is an interesting data, but in this context, doesn't not have a high effect.
Okay, but I think it's interesting to include them. Anyone else? Okay, we thank the speaker again.
Thank you.
Next speaker. Giovanni, sí, está acá, lo tenemos abierto. ¿Y tu nombre era, perdón? Ah, bien, buenísimo. Espera que lo tengo que abrir como PDF. Lo tengo que bajar y abrir como PDF. Ahí está, lo guardo. Ahí está. Ahora, ¿es así? Ahí está. Vos tenés media hora, ¿no?
Sí, pero
te
entonces
aviso.
20 minutos más 10.
¿Qué?
20 minutos más 10. Como 20 minutos más 10.
Exacto. Te aviso a los 20. Como que te faltan 5. ¿Te parece bien?
Creo que no voy a...
No, está perfecto. Cerrás ahí que... Okay, our next speaker is Graeme Candlish from Universidad de Valparaíso, and he will talk about cosmological simulation of a momentum coupling between dark matter and quintessence.
Okay. Well, first of all, I just wanted to say thanks to the organisers for giving me the chance to talk. So what I'm talking about today are cosmological simulations, a project using cosmological simulations to study these particular models of where dark energy is represented by a scalar field in the form of quintessence, and we have a coupling between that and dark matter. So this was work that I did with a master's student of mine, actually, Daniela Palma. And if you're interested in the paper, you can find it on the archive there. So to start with, I just wanted to give a bit of motivation and a bit of theoretical background for why we were interested in this. Then I'll talk about the simulations themselves, like how we set those up. I'll show you some highlights of the results, and then what we could learn from it and what we tend to do in the future. So I often start my talks when I talk about models that are beyond lambda CDM with this comment, which is where we have lambda CDM, it works really well, it fits many cosmological observations. There's just two small problems with it. The first is we don't know what lambda is, and the second is that we don't know what CDM is. So apart from that, we're doing really well. So basically, it would be a good idea for us to consider other models. And in particular, dynamical dark energy models could be a good option to try to give a more kind of physical basis for where dark energy comes from, and quintessence is the model that we chose to look at. And if we have a coupling in the dark sector, that might help to alleviate some cosmic tensions, such as the Hubble tension, sigma 8 tension, and some of the things that we've heard about in other talks. So in terms of the actual model that we were looking at, it's based on work that was published a while ago now by Portsiru and Skordis, where they classified models where you had a scalar field coupled in various ways to dark matter represented as a perfect fluid. They had 3 different types of models depending on how that coupling worked. So you can have a sort of standard density type coupling, but we were interested in what they referred to as the type 3 models, where the coupling appears with this term here, with this Z term, where you have the 4 velocity of the perfect fluid that represents the dark matter is coupled to the derivative of the scalar field. So the stress energy tensor for these models can be written in this fairly general form, where the function f is just some function of the standard kinetic term of the scalar field, the coupling term, and the scalar field itself. So if we want to look only at coupled quintessence, then the form of that function is quite simple. You have just the standard terms that you would have for a normal scalar field. So you have a kinetic term and the potential term, and then you have this final third term where you have the coupling. And we followed what they did in terms of choosing the form of that coupling. So we have gamma of z is just gamma 0, which is our coupling constant, multiplying z squared. Okay, so I'm going to skip over a lot of the derivation here because I don't think it's all that interesting to see all the details. But we worked in the Newtonian gauge. We looked at the perturbations in Newtonian gauge, and the thing about cosmological simulations is that we work in a Newtonian limit, actually. So we work in the limit of weak fields and low velocities, so velocities that are much lower than the speed of light. So taking all that into account, we finally find this expression, which is, of course, the Euler equation for the dark matter. And this is what's actually used in the cosmological n-body simulations. This is how we evolve the dark matter particles. In this model, what we have are these terms, H1, H2, and H3, which depend on the background scalar field due to the coupling, and these modify the Euler equation. So basically, we have a kind of a modification of the effective gravitational force that the dark matter experiences, and we also have, we can divide throughout by this, so we just have these two terms as basically containing the modification, and we see that we also have a modified cosmological friction term. Okay, so, and just for completeness, the background scalar field satisfies an equation which is almost a standard Klein-Gordon equation. It's really just a kind of overall rescaling of the field. So, taking all that into account, then we can actually put this into the n-body simulations. So the first thing that we did was we chose positive coupling. The coupling is somewhat constrained in the sense that if we have a coupling that's equal to 1/2, then the theory actually has a strong coupling problem. It's not constrained at all for negative values, but to start off with, we looked at the positive range. And in order to do cosmological simulations, you have to generate an initial power spectrum or an initial transfer function of the cosmological perturbations, and that's done with these kinds of Boltzmann codes like class and CAM. We use those to generate that initial power spectrum and also to calculate the background evolution of the scalar field. And then we used a code that's called music to generate the actual particle distribution that we have to use in the simulation. And then finally, the n-body solution was found using a code called Ramesses. So this is the thing that we had to modify in order to incorporate this modified Euler equation. So the scalar field models that we looked at, well, basically we chose a few. We chose models A, B, and C, where the potentials differ a little bit. Some of the parameters are changed. It's basically just a kind of exploration of parameters, where what we tried to do was to have the background evolution look roughly like lambda CDM. And the n-body simulation parameters, just for completeness, we used 128 cubed particles in a 32 megaparsec box, and then we had higher particle number simulations as well, 256 cubed, but in larger boxes to be able to look at the linear scales, basically, to go to larger scales. The mass resolution and the force resolution in these simulations is not fantastic, but it's good enough for our purposes. So just to show how the background evolution looks, this plot is actually, it's the Hubble parameter as a function of redshift normalized with the lambda CDM value. So there's a slight difference actually just because the scalar field models don't give exactly the same background evolution as lambda CDM. But really for our purposes, what's more important is comparing between the uncoupled cases and the coupled cases. That's really what's of more interest to us. But nonetheless, with this, we can see that there's sort of deviations from the kind of evolution that we would see in lambda CDM. Okay, so what's happening in the Euler equation then with this coupling? What we have is, I haven't explained exactly what these C2 and C1 are, but they're related to the H1, H2, H3 parameters, okay? So they basically incorporate the modifications to the Euler equation. And so C1 has to do with this modification of the cosmological friction, and C2 has to do with the modification of the effective gravitational force that the dark matter experiences. So because this parameter C1 goes to negative values, what we actually have is a kind of, rather than cosmological friction, we have a kind of cosmological push, or that's what we refer to it as in the paper. So what does all this do to structure formation? Well, just to give you a visual indication of what's going on in the simulation, so these are density distributions for the simulation that used 128 cube particles. I meant to check last night exactly what's what column and what's what row, but I can't actually remember, but it doesn't really matter because the point here is just to show you that they all look pretty much the same. And in the larger simulations with more particles, again, they all basically look the same. It doesn't matter too much which scalar field model we're looking at and what the coupling is, okay? But obviously we don't just look at these kinds of pictures, we look at the power spectra. So we calculate the power spectra for all these different models, and what we find is that I'm mainly going to concentrate on the most extreme case, so that was model C with the largest coupling that we chose, which was 0.3. What we find is that the coupling tends to significantly suppress structure formation on small scales, and it enhances it on larger scales. And looking at the simulations which were run on larger boxes, that's what these different lines are, it's all the same model, just changing the box size. We find that the results are basically convergent, if you like, on the larger scales. The difference at smaller scales here is simply because the resolution is changing, because we're changing the box size, okay? So that we can't really compare here, but we can check what's going on at the larger scales. Okay, so in order to try to pull apart what was going on in these models, we ran some other simulations where we effectively switched on only the modified cosmological friction term, that was referred to as C star 1. And we ran another model where only the modified gravitational force term was included. And these curves here, these lines in the graph, are normalized with yet another model which has the same background dynamics as the model with coupling, but we don't modify the Euler equation. That's just to make sure that we're kind of eliminating any change in the background evolution in our comparison. And what we see is that the cosmological push is basically expelling structure from the smaller scales, which is what we would expect, and the gravitational enhancement is leading to this overproduction of structure at those scales. But it's this modified cosmological friction term that seems to kind of win out and produce this overall effect when we include both modifications. So another thing that we can look at in cosmological simulations, of course, is what happens to the dark matter halos. So just for those that maybe are not so familiar with this, when we have dark matter collapsing into virialized structures in a cosmological simulation, we can basically fit a density profile to that dark matter, and we find that in simulations that density profile corresponds to a near universal profile, which is referred to as Navarro-Franken-White, which looks like this. And there's a scale radius here, which is related to the overall radius of the halo, kind of an arbitrary cutoff that we choose, but we can basically say, okay, if the density is if the density drops below 200 times the mean density or something like that, then we say that's the cutoff of the halo. And the relationship between that virial radius and the scale radius is given by the concentration parameter. So the only reason I'm talking about all of this is because we can use this concentration parameter to have an indication of how much dark matter is accumulating in the very centers of the halos. And this is what we find for the models where we separate out the different effects. So we have this sort of baseline model where we don't modify the Euler equation. And comparing to that, we can see that the enhanced gravitational force or effective gravitational force term increases the concentration quite appreciably, whereas the cosmological sort of push, if you like, is decreasing that central concentration. Okay, so one thing which came out of all this, which was a little bit surprising, is that we found that the substructure dynamics can actually be affected in a fairly non-trivial way by the inclusion of these modifications. So what I've got here is this is the model where we don't have any modification of the Euler equation, and we're looking at just sub-halos, so substructure within a massive host halo, like a big galaxy cluster. And what we find is that the velocity distribution of these substructures is basically continuous. It doesn't have any kind of separation. And that's the same situation that we have when we have this enhanced gravitational force as well. We see more structure because of the enhancement of gravity, but the velocity distribution is continuous. Whereas this cosmological push term is creating this kind of very strongly bimodal distribution in the velocities. So it seems that these models might have implications for how mergers would proceed in mergers of galaxy clusters, for example, how they would behave, and basically the sort of phase space distribution that we might expect to see in the substructure. So just to conclude, I've no idea how long I've taken, but I think it's been within time. Good, good. I know we're all hungry, so. So we were looking, as I said, at positive coupling. So in that case, we have this reduction of structure on small scales and an increase at large scales. We reduce the inner density profiles in our most massive halos, which I've tried to sort of show with the concentration parameter. This point here actually is quite relevant for people that work more in the kind of astrophysical side of cosmology, because there's a well-known problem in cosmological simulations which is called the cusp core problem, where the inner profiles of dark matter halos in simulations are much steeper than they appear to be in the observations. So these models might have something to say about that as well. We have this enhancement of the particle velocities within the halos and the substructure. So again, the phase space is definitely being fairly substantially changed. And as I mentioned, this bimodality could indicate, it could perhaps be a kind of more discriminatory signature of these kinds of models, perhaps, because it might affect how cluster mergers would behave. So that's something that we're looking at a bit more now, trying to run more simulations, get a more statistical handle on how frequent that effect is, and if it's something that could be usefully observed. And just to finish off, a little bit of kind of advertising, I suppose, but if any students here are interested in working in computational cosmology or numerical relativity, where we use these kinds of simulations or these kind of traditional numerical techniques, and also machine learning sort of techniques, like the kind of thing that Greco, my PhD student, was mentioning, then send me an email and you can come to Valpo. All right. Thanks very much.
Thanks for the nice talk. Questions?
Thanks, Grimme. So since you did mention this cusp core and also the missing satellite problems. So are they still, are they still a hot topic in this?
Okay, it's one that, yes, it is still a hot topic, but it's one of these things where it depends on who you talk to, whether it's solved or not. So there are quite a lot of people that say that it's solved just by including the baryonic physics. So that's feedback mechanisms from supernova and AGN and things like that, that they are sufficiently powerful to eject dark matter from the inner regions of the halos. But there are others that say that that can't work because the cusp core problem is actually most noticeable in the lowest mass halos. So there are some that say that there wouldn't actually be sufficient baryonic material in there to be able to eject enough dark matter to resolve the problem. So I would say it's still an open issue, but there are quite a few people that work on, like illustrious level simulations where they include all the hydrodynamics and they say, no, we've resolved it with that. But I would say it's still a bit controversial. The gamma zero, yeah, if it's equal to 1/2, yeah. Yes, yeah, you have a strong coupling problem. Yeah, I mean, you can see that from, just from the, as an example, from the Klein-Gordon equation. Yeah, you can see it there. Yeah. Yeah. So, I mean, actually, there was some work, the same Alquistis Porciru, she did some work using these models where they looked at negative coupling, and actually at the linear scales they said that this could be very useful for alleviating the sigma 8 tension. So one of the things I also want to do is obviously extend this work to negative values of the coupling and see how that. Gamma zero, no, I mean I can't, well I'd have it below that, yeah. Yes. Yeah. I haven't really explored, if you like, far closer and closer to value of 1/2, no. But I would assume that, yeah, you'll start to see very, very significant behavior. Yeah.
Anyone else? I have a couple of questions. So your simulations are dark matter only?
Yes.
Okay. And do you suppose that including baryons will vary your results?
It's a really good question because the thing is that obviously including baryons, the baryons are not affected by the coupling. So it's something that would be interesting to look at to see how the hydrodynamics behave when the dark matter, there's like could be in principle quite a strong difference between the kind of phase-based distribution of the dark matter and the baryon. So yeah, it's something that would be good to look at. The problem with running hydrodynamical simulations is that it just takes a lot longer, they're much more expensive. So.
I know. And if it's not too long, could you mention what the machine learning techniques are you currently using, or it's just a plan to use them in the future?
Sorry?
What machine learning techniques are you using, currently using?
Well, I mean, well, actually, Greco mentioned some stuff during his talk where we're using machine learning techniques to try to generate cosmological realizations, or at least to try to improve the results that come out of these kind of approximate solvers, so like COLA and these kinds of methods. But I'm also interested in, well, what we talked about, actually using these physics-informed neural networks, like trying to use neural networks to actually generate a density distribution, like a cosmological realization. I'm not too sure how to go about doing that, but it's something that we're interested in.
Okay, thank you. Anyone else? So we thank the speaker again.
Thank you.
And the last speaker of the morning? We have no last speaker. Okay. So we are going to lunch and we come back. Giovanni, at what time? 45. Okay. Okay, let's see you after lunch.